How does group K-fold differ from stratified K-fold in scikit-learn? Group K-fold considers the order of data points for splitting, while stratified K-fold focuses on preserving class distribution. Group K-fold ensures that data points belonging to the same group are not split across different folds, while stratified K-fold maintains the class distribution in each fold. Group K-fold focuses on preserving the class distribution in each fold, while stratified K-fold ensures that data points belonging to the same group are not split across different folds. Both A and B are correct. Group K-fold considers the order of data points for splitting, while stratified K-fold focuses on preserving class distribution. False. This statement is incorrect. Group K-fold doesn't prioritize the order of data points but ensures that data points from the same group remain together within the folds. Stratified K-fold focuses on maintaining the class distribution across the folds, not the order of data points. Group K-fold ensures that data points belonging to the same group are not split across different folds, while stratified K-fold maintains the class distribution in each fold. True. This statement correctly describes the key difference between group K-fold and stratified K-fold. Group K-fold preserves group integrity, ensuring that data points within a group remain within the same fold. Stratified K-fold prioritizes maintaining the class distribution across each fold, ensuring each fold has a representative sample of all classes. Group K-fold focuses on preserving the class distribution in each fold, while stratified K-fold ensures that data points belonging to the same group are not split across different folds. False. This statement is incorrect. It reverses the roles of group K-fold and stratified K-fold. Group K-fold is designed to preserve group integrity, not class distribution. Stratified K-fold focuses on preserving class distribution, not group integrity. Both A and B are correct. False. This statement is incorrect because statement A is incorrect. B. Imagine analyzing customer data where each customer has multiple transactions. Using group K-fold, you can ensure that all transactions from the same customer are kept within the same fold, preventing information leakage across folds during cross-validation. Let's consider a dataset with customer purchase history. Each customer has multiple transactions. Using group K-fold with customer ID as the grouping factor, we can ensure that all transactions for a particular customer are kept within the same fold. This prevents information leakage where a customer's purchase history might be used in both training and testing during cross-validation, leading to biased results. This is especially crucial when modeling customer behavior, as past transactions can influence future purchases. In a fraud detection dataset with a small percentage of fraudulent transactions, using stratified K-fold ensures that each fold has a similar proportion of fraudulent and non-fraudulent transactions, allowing for a fair evaluation of the model's ability to detect fraud. Consider a dataset with financial transactions, where only a small percentage are fraudulent. Applying stratified K-fold with fraudulent as the class label, we can create folds that maintain a similar ratio of fraudulent to non-fraudulent transactions. This ensures that our model is evaluated on folds that accurately reflect the real-world imbalance in the data. Without the stratification, the model might perform well on folds with a disproportionately higher number of non-fraudulent transactions, leading to an overestimation of its fraud detection accuracy. Cross-validation, a technique for evaluating the performance of a machine learning model by splitting the data into multiple folds and using each fold as a testing set while training on the remaining folds. Imagine training a model to predict house prices. We could use 5-fold cross-validation. Split the dataset into 5 folds. Train the model on 4 folds. And evaluate its performance on the remaining fold. Repeat this process for each fold, using a different fold as the testing set each time. This gives us a more robust estimate of the model's performance than using a single train test split. K-fold, a basic cross-validation technique that randomly splits the data into K-folds. Each fold is used as a testing set once, while the remaining folds are used for training. Imagine a dataset of 100 data points. With K-fold K5, we would randomly split the data into 5 folds of 20 data points each. In the first iteration, we would train the model on 80 data points from 4 folds and test it on the remaining 20. We would repeat this, using a different fold as the testing set in each iteration. Stratified K-fold, a cross-validation method that ensures each fold has approximately the same proportion of data points from each class as the original dataset. This is useful for dealing with imbalanced datasets. Imagine a dataset of 100 customer reviews. 80 are positive and 20 are negative. Using stratified K-fold with 5 folds, we would ensure that each fold has roughly 80 positive and 20 negative reviews. This prevents folds from having disproportionate class representations, leading to a more balanced evaluation. Group K-fold, a cross-validation method that ensures data points belonging to the same group are not split across different folds. This is useful when there are dependencies or relationships between data points within groups. Imagine a dataset of student exam scores where each student has multiple test scores. Using Group K-fold, we ensure that all test scores from the same student are kept within the same fold. This prevents information leakage, where scores from the same student might be used in both training and testing, leading to an overestimation of the model's accuracy. You want to perform cross-validation on a dataset with 1000 samples. Dividing it into 5 folds, you need to ensure that samples belonging to a specific group, e.g., gender, are distributed evenly across all folds. Which sklearn model selection class would you use? A. K-fold. B. Stratified K-fold. C. Group shuffle split. D. Time series split. E. All of the above. C. Group shuffle split. True. The group shuffle split class is specifically designed for this purpose. It allows you to define groups within your data and ensures that samples from the same group are not split into different folds. This preserves the group structure during cross-validation, leading to more reliable results, especially in situations where the group variable is strongly correlated with the target variable. False. K-fold divides the data into folds without considering any group structure. It might split samples from the same group into different folds, potentially leading to biased results if the group variable is important. False. Stratified K-fold focuses on maintaining the proportion of classes in the target variable within each fold. It doesn't handle group structure, so samples from the same group could still be split across folds. False. Time series split is designed for time series data, where the order of samples is crucial. It doesn't take into account group structure for general datasets. False. Only group shuffle split is the correct answer. The other options don't provide the specific functionality of ensuring even group distribution across folds. Imagine you are building a model to predict customer churn. Your data includes customer demographics, purchase history, and their assigned account manager. You want to make sure that customers managed by the same account manager don't end up in different folds during cross-validation. Group shuffle split would ensure that customers managed by the same person are kept together in the same fold, preventing potential bias. A technique to evaluate the performance of a model by splitting the data into multiple folds and using each fold as a test set while training the model on the remaining folds. Data where samples belong to distinct groups based on a specific feature, e.g., gender, customer ID, product category. A cross-validation strategy that ensures samples from the same group are not split into different folds, maintaining group structure during validation. A basic cross-validation method that divides data into K folds and trains on K1 folds. Testing on the remaining fold. A variation of K-fold that ensures each fold has a similar proportion of each class in the target variable, preventing imbalanced datasets from skewing the model's performance. A specialized cross-validation method for time series data, where the folds are created based on time intervals to preserve the temporal order. Let's say you have 100 customers, with 50 belonging to Group A and 50 belonging to Group B. You want to perform 5-fold cross-validation using group shuffle split. Here's how the data might be divided into folds using group shuffle split. Fold 1. Group A 10 customers. Group B 10 customers. Fold 2. Group A 10 customers. Group B 10 customers. Fold 3. Group A 10 customers. Group B 10 customers. Fold 4. Group A 10 customers. Group B 10 customers. Fold 5. Group A 10 customers. Group B 10 customers. As you can see, group shuffle split ensures an even distribution of customers from both groups across all folds, making the cross-validation results more robust. What is the primary purpose of K-fold cross-validation in machine learning? A. To evaluate the model's performance on unseen data. B. To prevent overfitting during training. C. To select the best hyperparameters for the model. D. All of the above. Correct. K-fold cross-validation helps estimate the model's performance on unseen data. This is a crucial part of evaluating a machine learning model's ability to generalize to new examples. The model is trained on portions of the data and then tested on the remaining portions, which it has not seen before, providing an indication of how well it will perform in real-world scenarios. K-fold cross-validation is a powerful technique for model evaluation and hyperparameter tuning in machine learning. Correct. By splitting the data into folds and training on different subsets, K-fold cross-validation helps prevent the model from becoming overly specialized to the training data. This leads to better generalization to unseen data. It achieves this by ensuring that the model learns from a variety of data points and doesn't simply memorize the training set. Here's why all the above options are correct. LTBRGT LTBRGTA. Model evaluation LTBRGT LTBRGT LTBRGTB. Preventing overfitting LTBRGT LTBRGT LTBRGTC. Hyperparameter tuning. Correct. K-fold cross-validation can be used to optimize hyperparameter selection. You can evaluate multiple hyperparameter combinations on different folds of the data. The combination that yields the best performance across the folds is typically chosen as the optimal set for your model. This helps find a model configuration that is not just good on the training data but also generalizes well to unseen data. Here's why all the above options are correct. LTBRGT LTBRGTA. Model evaluation LTBRGT LTBRGT LTBRGTB. Preventing overfitting LTBRGT LTBRGT LTBRGTC. Hyperparameter tuning. Correct. K-fold cross-validation effectively serves all the aforementioned purposes, making it a valuable tool in the machine learning workflow. K-fold cross-validation is a powerful technique for model evaluation and hyperparameter tuning in machine learning. D. All of the above. Cross-validation is a technique used to evaluate the performance of a machine learning model. It involves splitting the data into multiple folds and training the model on different combinations of folds. This helps to estimate how well the model will generalize to unseen data. Model evaluation to assess the accuracy and reliability of a model on new data. Overfitting occurs when a model learns the training data too well, performing poorly on new data. This can happen when the model is too complex or when there is not enough data to train it properly. Model improvement to prevent a model from becoming overly specialized to the training data and improve its generalization performance. Hyperparameter tuning involves finding the best set of hyperparameters for a machine learning model. Hyperparameters are parameters that are not learned from the data during training but must be set by the user, optimizing model performance to find the optimal configuration of hyperparameters that leads to the best model performance. sklearn, model selection. K-fold is a class in scikit-learn that provides a way to implement K-fold cross-validation. It allows you to easily create K-fold splits of your data, making it convenient for training and evaluating your machine learning model. Data splitting for cross-validation to split your data into K-folds for use in K-fold cross-validation. Let's consider an example using K-fold cross-validation with 5 folds. Assume we have 100 data point samples. The data is divided into 5 folds, 20 samples each. We train the model on 4 of the folds and test it on the remaining fold. This process is repeated 5 times, with each fold acting as the test set once. The average performance across the 5 folds provides an estimate of the model's overall performance. On unseen data, you have a dataset of patients with medical records, categorized by their hospital. You want to train a machine learning model to predict patient outcomes. How would you ensure your model performs well on data from different hospitals? A. Use K-fold cross-validation with a large K value. B. Use leave one out cross-validation. C. Use leave one group out. D. Use stratified K-fold cross-validation. False. While K-fold cross-validation is a good general technique, using a large K value might not be ideal for our scenario. K-fold doesn't consider the grouping structure of the data based on hospitals. A large K value, while providing more folds for training and testing, could still lead to folds containing patients from the same hospital, thus not effectively evaluating generalization across different hospitals. It can be a valid approach if the hospitals are not the major grouping structure, but it wouldn't be ideal for the case explained. False. Leave one out cross-validation (LOOCV) is too computationally expensive for large datasets. It's also less effective in our scenario because it focuses on individual patients rather than hospital groups. We need to evaluate how well the model generalizes across different hospital populations, not just individual patients. True. Leave one group out is the ideal technique because it trains your model on data from all hospitals, except one, then uses the excluded hospital's data for testing. This process is repeated for each hospital, giving you a clear picture of how well your model generalizes across different hospital populations. False. Stratified K-fold is useful for maintaining class proportions in folds, which is helpful for imbalanced datasets. However, it doesn't specifically address the group structure of the data based on hospitals. While it's a good approach for dealing with class imbalances, it might not be the best choice for evaluating the model's performance across different hospitals. C. Use leave one group out. LOOCV is similar to leave one group out, but it uses individual data points instead of groups. It's extremely computationally expensive, especially for larger datasets. Training a model to predict the price of a house based on individual features of the house. 1000, 10000, 1500, 15000, 2000, 2000. In LOOCV, you'd train the model on all data points except one. For example, in the first iteration, you would train the model on the first and third data points, and then use the second data point for testing. This process is repeated for each data point, resulting in 3 iterations. K-fold divides the data into K-folds. It uses K1 folds for training and the remaining fold for testing. This is repeated K times, using different folds for testing each time. Predicting customer churn based on historical data, where you want to evaluate the model's performance across different customer segments. 1, 0, 2, 1, 3, 0, 4, 1, 5, 0, 6, 1. With K3, you would divide the data into 3 folds. In the first iteration, you would train the model on folds 1 and 2, and test on fold 3. This process is repeated for each fold, resulting in 3 iterations. Stratified K-fold is similar to K-fold but ensures the proportion of data points from each class is maintained across all folds. This is useful when dealing with imbalanced datasets. Detecting fraudulent transactions, where you want to ensure the model performs well on both fraudulent and legitimate transactions. 1, 0, 2, 1, 3, 0, 4, 1, 5, 0, 6, 1, 7, 0. In a stratified K-fold with K3, you would aim to have each fold contain approximately the same proportion of fraudulent and legitimate transactions. This helps ensure that the model is evaluated on a representative sample of data. Which of the following statements accurately describe the leave P groups out cross-validation technique in scikit-learn sklearn? It divides the data into folds, ensuring that samples belonging to the same group are always in the same fold. It preserves the group structure of the data during cross-validation, guaranteeing that samples from the same group are either all in the training set or all in the testing set. It is useful when dealing with data where groups are not independent. For instance, patients in a clinical trial with similar characteristics. It supports the use of a custom group identifier, allowing you to specify groups based on attributes in your dataset. All of the above. It divides the data into folds, ensuring that samples belonging to the same group are always in the same fold. Incorrect. This statement describes a different cross-validation technique. Not leave P groups out. Leave P groups out does not guarantee samples from the same group are always in the same fold. It aims to keep samples of the same group together, either in the training or testing set. It divides the data into folds, ensuring that samples belonging to the same group are always in the same fold. It preserves the group structure of the data during cross-validation, guaranteeing that samples from the same group are either all in the training set or all in the testing set. Correct. This is a key characteristic of leave P groups out. It ensures that samples within the same group are not split between the training and testing sets, preserving the inherent relationships within the data. It preserves the group structure of the data during cross-validation, guaranteeing that samples from the same group are either all in the training set or all in the Testing set. It is useful when dealing with data where groups are not independent. For instance, patients in a clinical trial with similar characteristics. Correct. Leave P groups out is particularly useful for scenarios where groups in the data are not independent. Like patients in a clinical trial who share similar characteristics. By keeping these related samples together, it avoids introducing bias due to artificially splitting them. It is useful when dealing with data where groups are not independent. For instance, patients in a clinical trial with similar characteristics. It supports the use of a custom group identifier, allowing you to specify groups based on attributes in your dataset. Correct. Leave P groups out provides flexibility by allowing you to define groups based on your data attributes. This enables you to tailor the cross-validation process to the specific grouping structure of your data. It supports the use of a custom group identifier, allowing you to specify groups based on attributes in your dataset. All of the above. Correct. All the statements accurately describe the leave P groups out cross-validation technique in scikit-learn sklearn. All of the above. All of the above. Cross-validation. A resampling technique used to evaluate model performance by splitting the data into multiple folds. Subsets. This helps in estimating the model's performance on unseen data, reducing the risk of overfitting. In a spam detection model, you can use cross-validation to split the email dataset into folds. Train the model on one fold and test it on the remaining folds. This gives you a more robust estimate of the model's ability to identify spam emails. Group structure. The presence of groups or categories within your data that might influence relationships between samples. These groups can be based on various factors, such as patient characteristics, community affiliation, or time periods. In a study of customer behavior, you might identify groups based on demographics, age, location, income, purchase history, or customer preferences. This understanding of group structure can help you tailor your marketing efforts. Group identifier. A custom specification defining how groups are determined within your dataset, e.g., a column containing patient IDs, community names, or timestamps. This allows you to define groups based on specific attributes in your data. In a financial dataset, you can define groups based on the customer's credit score, investment portfolio, or transaction history. This can help in understanding the risk profile of different customer groups. sklearn, model selection, leave P groups out. The function in scikit-learn responsible for implementing leave P groups out cross-validation. It takes the data and a group identifier as input and splits the data into folds, ensuring that samples within the same group are kept together. If you have a dataset with patient data and you want to perform cross-validation while preserving the patient's group structure based on their treatment type, you can use leave P groups out with the treatment type as the group identifier. Let's imagine a clinical trial dataset with patients grouped by their treatment type A, B, or C. We have 15 patients in total. 1, A, 2, A, 3, A, 4, B, 5, B, 6, B, 7, C, 8, C, 9, C, 10, A, 11, B, 12, C, 13, A, 14, B, 15, C. Using leave P groups out with n splits 2, we might get the following folds: 1, 2, 3, 10, 13, 4, 5, 6, 11, 14, 7, 8, 9, 12, 15, 7, 8, 9, 12, 15, 1, 2, 3, 10, 13, 4, 5, 6, 11, 14. Notice that in both folds, patients belonging to the same treatment group are either all in the training set or all in the test set. This ensures that the model learns from a consistent group structure. Which statement best describes the leave one out cross-validation strategy in scikit-learn's model selection module? A. In each iteration, a single data point is used as the test set, while all other data points form the training set. B. It divides the dataset into k equal folds and uses one fold as the test set in each iteration. C. It uses the entire dataset for training and then evaluates the model on a separate holdout set. A. In each iteration, a single data point is used as the test set, while all other data points form the training set. This statement accurately describes the leave one out loop cross-validation strategy. It's the core principle of this technique. Correct. A. In each iteration, a single data point is used as the test set, while all other data points form the training set. B. It divides the dataset into k equal folds and uses one fold as the test set in each iteration. This statement describes k-fold cross-validation, not leave one out. Incorrect. B. It divides the dataset into k equal folds and uses one fold as the test set in each iteration. C. It uses the entire dataset for training and then evaluates the model on a separate holdout set. This statement describes holdout validation, not leave one out. Incorrect. C. It uses the entire dataset for training and then evaluates the model on a separate holdout set. A. In each iteration, a single data point is used as the test set, while all other data points form the training set. Cross-validation. Leave P-out cross-validation. Holdout validation. K-fold cross-validation. Stratified K-fold. Model evaluation metrics. Leave one out cross-validation. Imagine you are building a medical diagnosis model using a small data set of patient records. To ensure your model isn't overfitting to specific patients, you could employ LU. It would train the model on all but one patient's data and then evaluate it on that single patient. This helps understand how well the model generalizes to individual patients. Let's say you have 10 patient records with features like age, symptoms, and diagnosis 0 or 1. You could use LU with a logistic regression model to predict diagnosis. In the first iteration, train the model on 9 patients' data and predict the diagnosis of the 10th patient. Repeat this for each patient, creating 10 separate predictions. The overall accuracy of your model would be the average of these individual predictions. K-fold cross-validation. If you have a larger dataset for image classification, you might use 5-fold cross-validation. The data is split into 5 folds, and each fold is used as the test set once while the remaining folds are used for training. This gives a more robust evaluation than holdout validation. Assume you have 50 images with features like pixel values and class labels. In 5-fold, you'd divide the images into 5 groups of 10 images. Train the model on 4 groups 40 images and test it on the remaining group. Repeat this for each group, and average the results to assess the model's performance. Holdout validation. For a simple initial evaluation of a sentiment analysis model, positive or negative, you could split your data into 80 for training and 20 for holdout testing. This helps get a quick understanding of the model's performance on unseen data. Stratified K-fold. If you are working with imbalanced data, e.g., fraud detection where fraudulent cases are rare, you might use stratified K-fold. It ensures each fold has the same proportion of fraudulent and non-fraudulent cases as the original dataset, leading to a more balanced evaluation. Model evaluation metrics. After cross-validation, you can use metrics like accuracy, precision, recall, and F1 score to evaluate the model's performance depending on the specific problem. For example, in a fraud detection scenario, recall is particularly important to minimize false negatives, missing fraudulent cases. Which of the following statements iterate true for sklearn leave one out cross-validation? A. It generates k folds, where k is the number of data points in the dataset. B. It ensures that each data point is used exactly once as a test sample and all the remaining data points are used as training data. C. It is suitable for smaller datasets where computational resources are a concern. D. All of the above. This statement is true. Leave one out cross-validation creates a fold for each data point in the dataset, resulting in k folds where k is the number of data points. A. It generates k folds, where k is the number of data points in the dataset. This statement is true. Leave one out cross-validation ensures that each data point is used exactly once as a test sample, and the remaining data points are used as training data. B. It ensures that each data point is used exactly once as a test sample and all the remaining data points are used as training data. This statement is true. While leave one out is highly precise, it can be computationally expensive for large datasets. However, it is suitable for smaller datasets because the computational cost is less significant. C. It is suitable for smaller datasets where computational resources are a concern. This statement is true as all the above statements are true regarding leave one out cross-validation. D. All of the above. D. All of the above. Cross-validation is a technique used to evaluate the performance of a machine learning model by splitting the data into multiple folds. The model is trained on a subset of the data and tested on the remaining data. This process is repeated multiple times, with different folds being used as the test set each time. Model selection cross-validation can be used to compare the performance of different machine learning models on a given dataset. Hyperparameter tuning cross-validation can be used to find the best values for the hyperparameters of a machine learning model. Performance estimation cross-validation can be used to estimate the generalization performance of a machine learning model. K-fold cross-validation is a type of cross-validation where the data is split into k-folds. The model is trained on k1 folds and tested on the remaining fold. This process is repeated k times, with each fold being used as the test set once. Model selection k-fold cross-validation can be used to compare the performance of different machine learning models on a given dataset. Hyperparameter tuning k-fold cross-validation can be used to find the best values for k hyperparameters of a machine learning model. Performance estimation k-fold cross-validation can be used to estimate the generalization performance of a machine learning model. Stratified k-fold cross-validation is a variation of k-fold cross-validation that ensures that k distribution of the target variable is preserved in each fold. This is important when the target variable is imbalanced. Model selection stratified k-fold cross-validation can be used to compare the performance of different machine learning models on a given dataset with an imbalanced target variable. Hyperparameter tuning stratified k-fold cross-validation can be used to find the best values for the hyperparameters of a machine learning model with an imbalanced target variable. Performance estimation stratified k-fold cross-validation can be used to estimate k Generalization performance of a machine learning model with an imbalanced target variable. Leave P-out cross-validation is a type of cross-validation where P data points are left out of K training set, and the model is trained on the remaining data points. This process is repeated for all possible combinations of P data points. Model selection leave P-out cross-validation can be used to compare the performance of different machine learning models on a given dataset. Hyperparameter tuning leave P-out cross-validation can be used to find the best values for K hyperparameters of a machine learning model. Performance estimation leave P-out cross-validation can be used to estimate the generalization performance of a machine learning model. Leave one-out cross-validation is a special case of leave P-out cross-validation where P is equal to 1. This means that each data point is used as a test sample once, and all remaining data points are used as training data. Model selection leave one-out cross-validation can be used to compare the performance of different machine learning models on a given dataset. Hyperparameter tuning leave one-out cross-validation can be used to find the best values for K hyperparameters of a machine learning model. Performance estimation leave one-out cross-validation can be used to estimate the generalization performance of a machine learning model. Shuffle split cross-validation is a type of cross-validation where the data is shuffled and then split into multiple folds. This helps to ensure that the folds are not biased by the order of the data. Model selection shuffle split cross-validation can be used to compare the performance of different machine learning models on a given dataset. Hyperparameter tuning shuffle split cross-validation can be used to find the best values for K hyperparameters of a machine learning model. Performance estimation shuffle split cross-validation can be used to estimate the generalization performance of a machine learning model. Time series split cross-validation is a type of cross-validation that is specifically designed for time series data. It splits the data into folds that respect the temporal order of the data. Model selection time series split cross-validation can be used to compare the performance of different machine learning models on a given time series dataset. Hyperparameter tuning time series split cross-validation can be used to find the best values for K hyperparameters of a machine learning model on a time series dataset. Performance estimation time series split cross-validation can be used to estimate the generalization performance of a machine learning model on a time series dataset. Group K-fold cross-validation is a type of cross-validation that is used when the data is grouped. It ensures that data points from the same group are not split into different folds. Model selection group K-fold cross-validation can be used to compare the performance of different machine learning models on a given dataset with grouped data. Hyperparameter tuning group K-fold cross-validation can be used to find the best values for K hyperparameters of a machine learning model on a dataset with grouped data. Performance estimation group K-fold cross-validation can be used to estimate the generalization performance of a machine learning model on a dataset with grouped data. Model selection is the process of choosing the best performing machine learning model for a given task. This involves evaluating the performance of different models on a given dataset and selecting K model that performs best. Choosing the right model for a given task. For example, if you are trying to predict the price of a house, you might choose a linear regression model. If you are trying to classify images, you might choose a convolutional neural network. Optimizing model performance. Model selection can be used to find the model that performs best on a given dataset. Improving the accuracy of predictions by choosing the best performing model. You can improve the accuracy of your predictions Model evaluation is the process of assessing the performance of a trained machine learning model on unseen data. This involves evaluating the model's ability to generalize to new data and make accurate predictions. Assessing the performance of a model evaluation can be used to determine how well a model is performing on unseen data. Identifying areas for improvement. Model evaluation can help to identify areas where a model can be improved. Comparing different models. Model evaluation can be used to compare the performance of different models. sklearn model selection. Leave one out is a class in scikit-learn that provides an implementation of leave one out cross-validation. This class can be used to perform leave one out cross-validation on a given dataset. Performing leave one out cross-validation. sklearn model selection. Leave one out can be used to perform leave one out cross-validation on a given dataset. Evaluating the performance of a model. Leave one out cross-validation can be used to evaluate the performance of a machine learning model on a given dataset. Comparing different models. Leave one out cross-validation can be used to compare the performance of different models. 1, 2, 3, 4, 5. Let's take a dataset with 5 data points. In leave one out, we'll create 5 folds. For each fold, one data point will be the test sample, and the remaining data points will be the training data, x20. For example, in the first fold, data point 1 will be the test sample, and data points 2, 3, 4, and 5 will be the training data. In the second fold, data point 2 will be the test sample, and data points 1, 3, 4, and 5 will be the training data, and so on. 1, 2, 3, 4, 5, 2, 1, 3, 4, 5, 3, 1, 2, 4, 5, 4, 1, 2, 3, 5, 5, 1, 2, 3, 4. Which of the following best describes the leave P-out LPO cross-validation technique? A. It uses all but one data point for training and the remaining one for testing. B. It randomly splits the data into k folds and iterates through each fold, using k1 folds for training and 1 fold for testing. C. It creates all possible combinations of p data points for testing, using the remaining data for training. D. It is a variant of leave one out LU where a small portion of the data is left out for testing. A. It uses all but one data point for training and the remaining one for testing. False. This describes the leave one out LU cross-validation technique, not leave P out LPO. LU takes one data point at a time for testing, whereas LPO involves selecting combinations of multiple data points for testing. Leave one out LU. B. It randomly splits the data into k folds and iterates through each fold, using k1 folds for training and 1 fold for testing. False. This describes the k-fold cross-validation technique. LPO doesn't involve random splitting, it systematically creates all possible combinations of p data points for testing. K-fold cross-validation. C. It creates all possible combinations of p data points for testing, using the remaining data for training. True. This is the accurate definition of leave P out LPO. It exhaustively considers every possible group of p data points for testing, making it computationally expensive but potentially very rigorous. Leave P out LPO. D. It is a variant of leave one out LU where a small portion of the data is left out for testing. False. LPO is not a variant of LU. While LU leaves out one data point at a time, LPO leaves out multiple data points p in different combinations. Leave one out LU. C. It creates all possible combinations of P data points for testing, using the remaining data for training. Leave P out LPO. A cross-validation technique where all possible combinations of P data points are selected for testing, with the remaining data used for training. The number of folds is determined by P, resulting in a large number of folds, especially when the dataset is large. Small datasets when you have limited data points. LPO ensures you utilize most of the data for training, providing a more comprehensive performance evaluation. High-stakes decisions in situations where a model's performance is crucial. LPO's exhaustive testing can help identify any weaknesses or biases that other methods might miss. Let's say you have a dataset with 10 data points, and you want to use Leave 3 out LPO, P3. You would create all possible combinations of 3 data points for testing. This results in 10C3120 folds, where each fold uses 7 data points for training and 3 for testing. Each fold will provide a performance evaluation of your model, and averaging these evaluations gives you a robust estimate of the model's generalization. Performance cross-validation. A technique to evaluate the performance of a machine learning model by splitting the data into training and testing sets multiple times. This helps in assessing the model's ability to generalize to unseen data and reduce overfitting. Model evaluation. You can use cross-validation to get a more reliable estimate of your model's performance on unseen data compared to just a single train test split. Hyperparameter tuning. Cross-validation helps you select the best hyperparameters for your model by comparing the performance of different parameter combinations. Leave 1 out LU. A special case of LPO where P1, meaning one data point, is left out for testing in each fold. It offers the most rigorous evaluation but can be computationally expensive for large datasets. Small datasets. LU is suitable for small datasets where computational cost is not a concern. High variance models. LU can help identify overfitting issues in models that are highly susceptible to variance. Imagine you have a dataset with 5 data points. In LU, you would create 5 folds, each using 4 data points for training and 1 for testing. For instance, fold 1 would train on data points 2, 3, 4, and 5 and test on data point 1. This process is repeated for each data point as the test set. K-fold cross-validation splits the data into K-equal-sized folds. In each iteration, one fold is used for testing, and the rest are used for training. This is repeated K times. It provides a good balance between computational cost and model evaluation accuracy. Large datasets. K-fold is a popular choice for larger datasets because it strikes a balance between computational efficiency and evaluation accuracy. Model comparison. You can use K-fold to compare different machine learning models on the same dataset, ensuring a fair evaluation. Suppose you have a dataset with 20 data points and choose K5 for 5-fold cross-validation. You split the data into 5 groups of 4 data points each. In the first fold, data group 1 is used for testing, and groups 2, 3, 4, and 5 are used for training. This process is repeated 5 times, with each group being the testing set once. The average performance across all 5 folds provides an estimate of the model's performance. Sklearn model selection provides a variety of cross-validation techniques, including LPO, LU, and K-fold, for evaluating machine learning models. Cross-validation implementation. The sklearn library in Python offers convenient functions to implement various cross-validation techniques. Model tuning and evaluation. You can use sklearn's cross-validation tools to optimize hyperparameters and assess the performance of your models. Which of the following statements about the sklearn predefined split class is true? A. It allows you to split data into folds based on a predefined array of indices. B. It is used for cross-validation, but instead of randomly splitting data, it uses a predetermined array of indices. C. It is particularly useful for time series data, where you want to ensure that the data is split chronologically. D. All of the above. True. The primary function of predefined split is to define custom folds based on a user-provided index array. A. True. The primary function of predefined split is to define custom folds based on a user-provided index array. True. Predefined split is used in cross-validation. It overrides the standard random splitting mechanism by utilizing your provided index array to define the folds. B. True. Predefined split is used in cross-validation. It overrides the standard random splitting mechanism by utilizing your provided index array to define the folds. True. This is a significant use case for predefined split. In time series data, maintaining chronological order is essential to avoid data leakage from the future to the past. C. True. This is a significant use case for predefined split. In time series data, maintaining chronological order is essential to avoid data leakage from the future to the past. True. All the above statements are accurate, making D the correct answer. The correct answer is LTBGT. D. All of the above. A technique for evaluating the performance of a machine learning model by splitting the data into multiple folds and training and testing the model on different combinations of folds. Imagine you are building a model to predict customer churn. Instead of just splitting the data once into train and test sets, you might use 5-fold cross-validation. The data is split into 5 folds, and the model is trained 5 times, each time using 4 folds for training and 1 fold for testing. This helps assess the model's robustness and generalizability across different parts of the data. When information from the test data is inadvertently included in the training data, leading to an overly optimistic evaluation of the model's performance. Let's say you are predicting house prices. If you accidentally include the house price in your training data, your model will learn to perfectly predict the price. This is data leakage because it's using information that wouldn't be available in a real world scenario. A class in sklearn, model selection, that allows you to define your own custom splitting strategy for cross-validation using a predefined array of indices. In time series data, we might use the predefined split class to ensure that data is split chronologically. For example, we might define folds where each fold represents a specific period in time. This helps avoid data leakage from the future to the past, which is crucial for accurate model evaluation. Which of the following options best describes the functionality of scikit-learn's repeated k-fold cross-validation technique? A. Repeated k-fold performs stratified k-fold cross-validation. B. Repeated k-fold performs k-fold cross-validation multiple times with different random splits each time. C. Repeated k-fold performs leave one out cross-validation. D. Repeated k-fold performs k-fold cross-validation with shuffling and stratification. E. All of the above. A. Repeated k-fold performs stratified k-fold cross-validation. While repeated k-fold can be used with stratification, it's not inherent to its functionality. It performs k-fold cross-validation multiple times with different random splits, regardless of stratification. False. B. Repeated k-fold performs k-fold cross-validation multiple times with different random splits each time. Repeated k-fold repeats the process of splitting the data into k-folds multiple times, each time with a different random shuffle. This helps to ensure that the model's performance is not overly influenced by a single random split. True. C. Repeated k-fold performs leave one out cross-validation. Repeated k-fold is an extension of k-fold cross-validation, not leave one out cross-validation. Leave one out cross-validation involves using all but one sample for training and the remaining for testing, which is different from the k-fold approach. False. D. Repeated k-fold performs k-fold cross-validation with shuffling and stratification. While repeated k-fold can incorporate shuffling and stratification, it's not always necessary. Its core functionality is to repeat k-fold cross-validation with different random splits. Shuffling and stratification are optional enhancements. True. E. All of the above. Repeated k-fold performs k-fold cross-validation multiple times with different random splits. It can optionally include shuffling and stratification. And while it can be used with stratified data, it doesn't inherently perform stratified cross-validation. Therefore, all of the above statements are true. True. A. 1. K-fold cross-validation. A common cross-validation technique that splits the dataset into k-fold subsets. The model is trained on k1 folds and tested on the remaining fold. And this process is repeated k times, with a different fold being used for testing each time. This allows for a more robust evaluation of the model's performance. In a machine learning project to predict customer churn, k-fold cross-validation can be used to split the customer data into, for example, 5 folds. The model would be trained on 4 folds and tested on the remaining fold. Repeated 5 times with a different fold for testing each time. This would give a better estimate of the model's performance than just training on all the data and testing on a single holdout set. 2. Stratification. A technique used in cross-validation, particularly in imbalanced datasets, to ensure that the class proportions within each fold are representative of the overall dataset. This helps prevent bias when evaluating models, as the model's performance might be misleading if the folds don't accurately reflect the class distribution in the data. In a medical diagnosis project predicting whether a patient has a specific disease, where the disease is rare, stratification would be crucial. Using stratified k-fold, we can ensure each fold has the same proportion of patients with and without the disease as in the original dataset. This would help to ensure that the model is not overly influenced by the majority class and can generalize well to new data. 3. Shuffling. The process of randomly rearranging the order of the data before splitting it into folds. This helps to avoid biases introduced by the order of the data. For example, if the data is sorted by a feature, shuffling helps ensure that the folds are not biased towards specific values of that feature. In a project to predict house prices, shuffling the dataset before splitting it into folds would be beneficial. This helps to avoid biases related to the order in which the data was collected, ensuring that the folds are representative of the overall price distribution. 1. Model selection. Repeated k-fold is a valuable tool for evaluating and comparing different machine learning models. By providing more reliable estimates of their performance, it helps to select the best model for a particular task. This is achieved by averaging the performance metrics across multiple repetitions of the k-fold. Cross-validation. Imagine you are building a spam filter. You have 2 candidate models, a logistic regression and a support vector machine. Repeated k-fold can help you evaluate both models' accuracy, precision, and recall across multiple random splits of the data. Based on the average performance across the repetitions, you can choose the model that consistently performs better for your spam filtering task. 2. Hyperparameter tuning. Finding the optimal hyperparameters for a machine learning model is essential for achieving best performance. Repeated k-fold can improve the reliability of hyperparameter tuning by reducing the impact of specific data splits. By running the tuning process multiple times with different splits, you get a more robust assessment of the hyperparameter's effectiveness. In a project to build a recommendation system, you might need to tune the regularization parameter of a linear regression model. Using repeated k-fold, you can experiment with different values of the regularization parameter, and the results will be averaged across multiple splits. This helps identify the regularization strength that yields the best performance, reducing the risk of choosing a value that works well on a single split but not on the entire dataset. 3. Assessing model stability. Repeated k-fold can help determine how stable the model's performance is across different data splits, providing insights into its generalization ability. A model with stable performance across different splits is likely to generalize better to unseen data. In a project to build an image classification model, you might use repeated k-fold to assess how well the model performs on various image datasets. If the model's performance is consistent across multiple repetitions of the cross-validation, it suggests that the model is robust and not overly influenced by specific image features or data splits, which is the main purpose of the repeated stratified k-fold cross-validation technique in scikit-learn. sklearn, to ensure that each fold contains approximately the same proportion of samples from each class in the target variable, repeated for a specified number of times. To split the dataset into k-folds, where k is the number of folds, and each fold is used as a test set, repeated for a specified number of times. To create multiple random splits of the dataset, ensuring that each fold has a random distribution of samples, repeated for a specified number of times. All of the above, to ensure that each fold contains approximately the same proportion of samples from each class in the target variable, repeated for a specified number of times. Correct. This is a core function of repeated stratified k-fold. It aims to maintain class distribution within each fold, ensuring a balanced representation of all classes in the target variable. To split the dataset into k-folds, where k is the number of folds, and each fold is used as a test set, repeated for a specified number of times. Correct. This is a fundamental aspect of k-fold cross-validation, which is the basis of repeated stratified k-fold. The dataset is divided into k-folds, and each fold serves as a test set in turn. To create multiple random splits of the dataset, ensuring that each fold has a random distribution of samples, repeated for a specified number of times. Correct. The repeated part of the technique involves performing this stratified k-fold split multiple times, generating different random splits of the data. This helps to reduce the variance in model evaluation. All of the above. Correct. The repeated stratified k-fold method encompasses all these aspects. It combines stratified k-fold splitting to maintain class balance, the typical k-fold structure, and the repetition of these splits for more robust evaluation. D. Cross-validation. A technique to evaluate a model's performance by splitting the dataset into multiple folds, training on a subset of folds and testing on the remaining fold. Imagine you have 100 data points and want to train a model. You could split them into 5 folds, 20 points each. Train the model on 4 folds and test it on the remaining fold. Repeating this 5 times to get an average performance estimate. K-fold cross-validation. A specific type of cross-validation where the dataset is split into K-folds. And the model is trained and evaluated K times. Each time using a different fold as the test set. Continuing the previous example, with 5 folds, you would train the model 5 times. Each time using a different fold as the test set. Stratified K-fold. A variation of K-fold cross-validation that ensures that each fold contains approximately the same proportion of samples from each class in the target variable. If you have a dataset with 2 classes A and B and 80 of your data is from class A, stratified K-fold would ensure that each fold also contains approximately 80 of samples from class A. Repeated stratified K-fold. A technique that performs stratified K-fold cross-validation multiple times, ensuring that each fold has a consistent proportion of samples from each class. Reducing the variance in the model evaluation. You might perform stratified K-fold 10 times, each time creating a different set of folds. This helps to reduce the impact of random variations in the data split on the model evaluation. Medical diagnosis. Analyzing medical data where rare conditions can be present, e.g., predicting a specific disease based on patient data. Ensuring that each fold contains a representative sample of both common and rare conditions. In a study of heart disease, repeated stratified K-fold would ensure that each fold includes a proportional representation of patients with and without heart disease, even if heart disease is a relatively rare condition. Fraud detection. Identifying fraudulent transactions in financial data, where fraudulent cases might be much fewer than legitimate transactions. Maintaining the balance of classes in each fold. In a dataset of credit card transactions, repeated stratified K-fold helps to create folds that accurately reflect the low percentage of fraudulent transactions, allowing for more reliable model training and evaluation. Sentiment analysis. Classifying text data based on sentiment positive, negative, neutral, ensuring that each fold has a balanced representation of each sentiment category. Especially when dealing with datasets where one sentiment dominates. In a social media dataset where positive sentiment is prevalent, repeated stratified K-fold would ensure that each fold contains a fair share of positive, negative, and neutral sentiments, leading to more accurate sentiment classification. What does sklearn's shuffle split cross-validation strategy aim to achieve? A. Split data into train and test sets with a fixed size. B. Randomly shuffle the data before splitting into train and test sets. C. Create multiple train test splits, ensuring each sample is in a test set a fixed number of times. D. All of the above. A. Split data into train and test sets with a fixed size. False. While shuffle split does involve splitting data into train and test sets, it's not limited to fixed sizes. The test size can be adjusted as a parameter, allowing flexibility in the proportion of data allocated for training and testing. B. Randomly shuffle the data before splitting into train and test sets. True. Shuffle split indeed shuffles the data randomly before splitting. This randomization is crucial for preventing biases that might arise from the inherent order of data. For instance, if the data is sorted by a particular attribute, a non-shuffled split could lead to one set containing mostly samples from one class and the other set from another class. Shuffling ensures a more balanced distribution of samples across train and test sets. C. Create multiple train test splits, ensuring each sample is in a test set a fixed number of times. True. Shuffle split implements cross-validation, meaning it generates multiple train test splits. The key feature of shuffle split is its ability to control how many times each sample appears in a test set. This parameter, often specified as n splits, helps ensure that the model gets a chance to learn from all samples in the data and reduces the risk of overfitting by preventing the model from relying too heavily on specific subsets of the data. D. All of the above. True. As explained above, shuffle split combines the features of randomly shuffling the data, creating multiple train test splits, and ensuring each sample appears in the test set a fixed number of times. Therefore, option D is the correct answer. D. All of the above. Cross-validation, a resampling technique used to evaluate the performance of a machine learning model on unseen data. It involves splitting the dataset into multiple subsets, using some subsets for training and others for testing, and then averaging the results to get a more robust estimate of the model's generalization ability. Evaluating different models to select the best performing one. Choosing the optimal hyperparameters for a model to avoid overfitting. Train test split, a fundamental technique for splitting data into two sets: a training set used to train the model and a testing set used to evaluate the trained model's performance on unseen data. Evaluating model performance after training. Tuning model parameters to improve performance on unseen data. Data shuffling, the process of randomly reordering the data points in a dataset. This is often done to prevent biases that might arise from the inherent order of the data. Ensuring a balanced distribution of samples across train and test sets. Reducing the risk of overfitting by preventing the model from learning patterns specific to the order of the data. Model evaluation, the process of assessing the performance of a trained machine learning model using metrics such as accuracy, precision, recall, and F1 score. Determining the effectiveness of a model on a specific task. Comparing different models to identify the best performing one. Hyperparameter tuning, the process of finding the best set of hyperparameters for a machine learning model. Hyperparameters are settings that are not learned from the data but are set before training a model. Improving model performance by finding the optimal hyperparameter values. Reducing overfitting by choosing hyperparameters that minimize the model's complexity. From sklearn, model selection import shuffle split. From sklearn, datasets import load iris. X, Y lotteries return XE true. CV shuffle split N splits 5. Test size 0.2. Random state 42. For train index. Test index in CV. Split X. X train. X test X train index. X test index. Y train. Y test Y train index. Y test index. Train and evaluate your model using X train. Y train. X test. Y test. The code demonstrates how to use shuffle split to create 5 different train test splits with a 20 test size. The loop iterates through each split, providing the indices for training and testing data. You can then use this data to train and evaluate your model. What is the primary purpose of stratified k-fold in scikit-learn sklearn model selection? To ensure that each fold has a roughly equal number of data points. To maintain the original class distribution in each fold. To randomize the data splitting for better generalization. All of the above. True. This is one of the key goals of stratified k-fold. It tries to distribute the data points evenly across the folds, ensuring that no single fold gets disproportionately large or small, contributing to a fairer comparison of models trained on different folds. This addresses the point of equal data points per fold in the explanation section. True. The primary purpose of stratified k-fold is to preserve the class proportions of the original dataset within each fold. This is crucial for handling imbalanced datasets and ensuring that models are not biased towards specific classes. This relates to class distribution preservation in the explanation section. True. While stratified k-fold aims for equal fold sizes and class distribution, it still employs randomization within the stratification process. This helps to prevent overfitting and encourages better model generalization. This relates to randomization for generalization in the explanation section. True. The correct answer is D. All of the above. Stratified k-fold combines these three aspects to achieve a more robust and reliable cross-validation process, particularly when dealing with datasets containing distinct classes. D. All of the above. A technique used to evaluate machine learning models by dividing the data into folds and training testing the model on different combinations of these folds. This helps assess how well the model generalizes to unseen data and avoids overfitting. Evaluating the accuracy of a fraud detection model using different sets of financial transactions. Assessing the performance of a spam filter by testing it on various email datasets. Determining the effectiveness of a medical image classification model using different images from various patients. A specific type of cross-validation where the data is divided into k equal-sized folds. The model is trained on k1 folds and tested on the remaining fold. Rotating the testing fold across the k iterations. Training a recommendation system on a set of user data. Splitting it into 5 folds and evaluating the system's performance on each fold. Fine-tuning a sentiment analysis model by dividing a collection of product reviews into 10 folds and assessing its performance on each fold. Evaluating the efficiency of a natural language processing model by dividing a data set of news articles into 7 folds and testing its accuracy on each fold. A variation of k-fold specifically designed for datasets with distinct classes. It ensures that each fold maintains the same proportion of classes as the original dataset, making it especially useful for handling imbalanced datasets or classification problems. Training a credit risk assessment model on a dataset of loan applications, where the proportion of defaults should be preserved in each fold to avoid bias. Evaluating a customer churn prediction model by maintaining the original churn rate in each fold to ensure accurate performance assessment. Assessing the performance of a medical diagnosis model by ensuring that each fold contains the same ratio of healthy and diseased patients. Preventing biased evaluations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 3, 1, 2, 7, 8, 13, 14, 3, 4, 9, 10, 15, 16, 5, 6, 11, 12, 17, 18. In this example, the dataset is divided into 3 classes A, B, C with 6 data points each. We want to perform 3-fold stratified cross-validation. Notice how each fold has 2 data points from each class, maintaining the original proportion of 26/13 for each class. You have a dataset with 1000 samples, divided into 2 classes, 600 in class A and 400 in class B. You want to split it into training and testing sets while maintaining the class proportions. Which of the following options will achieve this using stratified shuffle split in sklearn? A. Stratified shuffle split n splits 1, test size 0.2, random state 42. B. Stratified shuffle split n splits 5, test size 0.2, random state 42. C. Stratified shuffle split n splits 10, test size 0.3, random state 42. D. All of the above. True. Stratified shuffle split n splits 1. Test size 0.2. Random state 42 will create a single split with 20 of the data in the testing set and 80 in a training set. Since stratified shuffle split ensures class proportions are maintained, the testing set will also have 60 of class A and 40 of class B, mirroring the original dataset. True. Stratified shuffle split n splits 5. Test size 0.2. Random state 42 will create 5 splits, each with 20 of the data in the testing set and 80 in the training set. Again, the class proportions will be preserved in each split, resulting in 60 of class A and 40 of class B in each testing set. True. Stratified shuffle split n splits 10. Test size 0.3. Random state 42 will create 10 splits, each with 30 of the data in the testing set and 70 in the training set. The class proportions will be preserved in each split, meaning each testing set will have 60 of class A and 40 of class B. True. As demonstrated above, each option correctly utilizes stratified shuffle split to ensure class proportions are maintained during data splitting, irrespective of the number of splits or the test size. Therefore, the correct answer is D. All of the above. D. All of the above. Stratified sampling. A sampling technique that ensures representation of all classes in the dataset in the sample, maintaining the proportions. Data splitting. The process of dividing a dataset into separate subsets for training, testing, and validation. Class proportions. The relative frequencies of different classes in a dataset. Training set. A subset of the data used to train a machine learning model. Testing set. A separate subset of the data used to evaluate the performance of a trained model. Random state. A parameter used to control the randomness of the data splitting process. It ensures consistent results for reproducibility. Scikit-learn sklearn. A popular Python library for machine learning, offering various tools and techniques, including data splitting methods, model selection, the process of choosing the best machine learning model for a given task based on performance. Evaluation. Image classification with imbalanced classes, ensuring equal representation of each class in both training and testing sets. Medical diagnosis with rare conditions, preserving the ratio of patients with the condition to those without it for accurate model. Evaluation. Fraud detection with low fraud rates, maintaining the low frequency of fraudulent transactions for reliable model performance. You are working on a machine learning project with data that has both class labels and group IDs. You want to perform cross-validation while ensuring that each fold has a representative distribution of both classes and groups. Which sklearn function would you use to achieve this? A. K-fold. B. Stratified K-fold. C. Group K-fold. D. Stratified group K-fold. D. Stratified group K-fold. Stratified group K-fold is the most suitable option because it ensures that both class distribution and group membership are preserved in each fold of the cross-validation. K-fold does not consider class labels or group memberships, so it might result in folds with uneven distributions of classes and groups. Stratified K-fold only ensures that the class distribution is maintained in each fold, but it doesn't account for group memberships. Group K fold only preserves the group membership in each fold. But it doesn't consider the class distribution. Medical data where patients belong to specific groups, e.g., age, gender, and have different disease outcomes. Social science studies where individuals belong to different social groups, e.g., income levels, and exhibit different behaviors. Recommender systems where users belong to different groups, e.g., demographics, and exhibit different preferences. Cross-validation. Stratification. Group K-fold. Stratified K-fold. K-fold. Model selection. sklearn. Stratified group K-fold. Which of the following options accurately describes how time series split works for splitting time series data into train and test sets? A. It randomly divides the data into train and test sets, ensuring a consistent time order. B. It splits the data based on a predefined ratio, e.g., 80 train, 20 test, ensuring data points in the test set are always later than those in the train set. C. It creates consecutive folds where each fold contains a contiguous block of data from the time series, preserving the temporal order and allowing for cross-validation. D. All of the above. False. This statement describes a random split, not time series split. Time series split is designed to preserve temporal order, not randomize it. False. While time series split ensures the test set is later than the train set, it doesn't necessarily use a predefined ratio. It focuses on creating consecutive folds for cross-validation. True. This is the accurate description of time series split. It splits the data into consecutive folds, each containing a block of data, maintaining the time series order. This is crucial for evaluating time series models, as it prevents leakage of information from the future into the past. False. This is incorrect because options A and B are not accurate representations of time series split. C. It creates consecutive folds where each fold contains a contiguous block of data from the time series, preserving the temporal order and allowing for cross-validation. Data that is ordered by time, where each data point is related to the previous one. Monthly sales figures for a company, daily stock prices, hourly temperature readings. A technique used to evaluate the performance of a machine learning model by splitting the data into multiple folds and using different folds as train and test sets. In a 5-fold cross-validation, the data is split into 5 equal parts. Each fold is used once as the test set while the remaining 4 folds are used as the training set. This process is repeated 5 times, and the average performance across all 5 folds is used to evaluate the model. Data points that are sequential and adjacent in the time series. In a time series of daily stock prices, a contiguous block could represent the prices for a week or a month. The order in which data points are collected over time. In a time series of monthly sales figures, the temporal order is crucial because it indicates the sequence in which sales occurred. Predicting future values based on past data, e.g., stock prices, weather patterns. Predicting the future price of a particular stock based on historical data. Forecasting the demand for a product in the next quarter based on past sales figures. Identifying unusual patterns in data, e.g., detecting fraudulent transactions, machine failures. Detecting unusual spikes in network traffic that could indicate a denial of service attack. Identifying patterns in sensor readings that suggest a machine is about to fail. Identifying patterns and trends in data over time, e.g., analyzing website traffic, sales trends. Analyzing website traffic data to identify seasonal trends in user behavior. Tracking sales data to identify periods of high or low demand. Analyzing the emotional tone of text data over time, e.g., monitoring customer feedback. Analyzing social media trends. Tracking social media sentiment around a brand or product to understand public perception. Analyzing customer reviews to identify areas for improvement. From sklearn, model selection, import time series split. TSCV time series split n splits 5. For train index, test index in TSCV, split x train, x test, x train index, x test index, y train, y test, y train index, y test index. This code snippet demonstrates how to use time series split in Python to create folds for cross-validation. It initializes a time series split object with 5 splits and then iterates through the folds, extracting the train and test indices for each fold. Analyzing data that is collected over time, identifying trends, patterns, and anomalies. A property of a time series where its statistical properties, e.g., mean, variance, remain constant over time. The correlation between a time series and its lagged values. Autoregressive integrated moving average models used for time series forecasting. A time series forecasting library that can handle seasonality and trend. What does the function lt_font style font size 16 px GTLTBGT sklearn model selection check CV LTBGT font TGT do in scikit-learn? A. It checks if the given cross-validation strategy is valid for the given dataset. B. It performs cross-validation and returns the best performing model. C. It checks the number of splits in a cross-validation strategy. D. All of the above. The function lt_font style font size 16 px GTLTBGT sklearn model selection check CV LTBGT font TGT is used to verify the validity of a cross-validation splitting strategy for a given dataset. It checks whether the strategy meets the requirements, including the number of splits, the data size, and whether the splits are distinct. It also performs checks on the validity of the cross-validation strategy itself. This function is crucial for ensuring that cross-validation is correctly implemented and A. Results are reliable. Correct. The function lt_font style font size 16 px GTLTBGT sklearn model selection check CV LTBGT font TGT does not perform cross-validation. It only checks the validity of the cross-validation strategy. The actual cross-validation is done using other functions like lt_font style font size 16 px GTLTBGT sklearn model selection crossval TBGTL20GT or lt_font style font size 16 px GTLTBGT sklearn model selection cross-validate TBGTL20GT. Incorrect. As part of verifying the validity of the cross-validation strategy, lt_font style font size 16 px GTLTBGT sklearn model selection check CV LTBGT font TGT checks A. Number of splits in the strategy. It ensures that the number of splits is consistent with the data size and other requirements. Correct. Since lt_font style font size 16 px GTLTBGT sklearn model selection check CV LTBGT font TGT performs all the checks mentioned in options A and C, and does not perform cross-validation as mentioned in option B. This choice is correct. Correct. D. All of the above. Cross-validation. It is a technique to evaluate the performance of a machine learning model by dividing the data into multiple folds and training the model on different combinations of folds. This helps in assessing the model's generalization ability. LT font style font size 16px sklearn, model selection, k-fold font EGT. A commonly used cross-validation technique that divides the data into k-folds. It uses k1 folds for training and the remaining fold for testing. It iterates through all possible combinations of folds. LT font style font size 16px sklearn, model selection, stratified k-foldlet font EGT. A cross-validation technique similar to k-fold but ensures that each fold maintains the same proportion of classes as the original dataset. This is crucial for datasets with imbalanced class distributions. LT font style font size 16px sklearn, model selection, leave one out, font EGT. A cross-validation technique where each data point is used as a test sample once, with the remaining data used for training. This is computationally expensive but provides a robust estimate of the model's performance. Error handling. When implementing cross-validation for model evaluation, it is essential to ensure that the chosen strategy is valid for the given data. LT font style font size 16px GT LTBGT check CV LTBGT LT font EGT helps in catching potential issues early on and avoiding unexpected errors. Model selection. When comparing different machine learning models, it's crucial to use the same cross-validation strategy for a fair evaluation. LT font style font size 16px GT LTBGT check CV LTBGT LT font EGT guarantees that all models are assessed using a valid and consistent splitting strategy. Let's say you have a dataset of 100 data points and want to perform 5-fold cross-validation. You can use LT font style font size 16px GT LTBGT sklearn, model selection, k-fold LTBGT LT font EGT2. Split the data into 5 folds, with each fold containing 20 data points. Before proceeding, it is good practice to use LT font style font size 16px GT LTBGT sklearn, model selection, check CV LTBGT LT font EGT to verify that LT font style font size 16px GT LTBGT sklearn, model selection, k-fold LTBGT LT font EGT strategy is valid. For this dataset, this will ensure that the chosen cross-validation strategy is appropriate for the data size and other requirements. Which of the following best describes the purpose of sklearn, model selection, train test split? A. To split data into equal-sized subsets. B. To create a balanced representation of classes within the data. C. To randomly partition data into training and testing sets. D. To perform cross-validation on a dataset. E. All of the above. NBSP 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 NBSPA. Equal-sized subsets. While the function aims for a balanced split, it doesn't guarantee perfectly equal sizes. The test size parameter controls the proportion of data allocated to the test set. The remaining data forms the training set. False. NBSP 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 NBSPB. Balanced class representation. The stratify parameter ensures that the class distribution in training and testing sets closely matches the original dataset. This is crucial for preventing bias when evaluating model performance. False. NBSP 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 NBSPC. Random partitioning. The core functionality of train test split is to randomly divide the data. Randomness helps in preventing biases and ensures the generalizability of model evaluations. False. NBSP 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 NBSPD. Cross-validation train test split isn't directly related to cross-validation, which is a technique used for evaluating models on multiple folds of the data. While you can use train test split to prepare data for cross-validation, it doesn't perform cross-validation itself. False. Solution. Train test split is a versatile tool for data partitioning. Here's why all the above choices are valid. True. All of the above. Training and testing sets. Data partitioning. Model evaluation. Randomization. Cross-validation. Class imbalance. Stratification. 1. Building predictive models separating data into training and testing sets is fundamental for developing and evaluating machine learning models. 2. Evaluating model performance. The test set is used to assess how well the trained model generalizes to unseen data, providing insights into its real-world effectiveness. 3. Hyperparameter tuning. By splitting data, you can train models with different hyperparameter settings on the training set and evaluate their performance on the test set to identify optimal configurations. Python. From sklearn, model selection. Import train test split. Xtrain, xtest, ytrain, ytest. Train test split x, y, test size 0.2, random state 42, age, income, education, loan approval, 30, 5000, bachelor's, yes, 25, 4000, high school, no, 45, 700, masters, yes, 28, 550, bachelor's, yes, 35, 600, masters, yes, 22, 350, high school, no, 40, 650, bachelor's, yes, 0.2, 42. In this example, we have a dataset of 7 individuals with features like age, income, and education. The target variable is loan approval, which is either yes or no. Using train test split with test size 0.2, we would randomly split the data into a training set 80 of the data and a testing set 20 of the data. This ensures that we have a portion of the data to train our loan approval prediction model in, another portion to evaluate its performance on unseen data. You are building a machine learning model to predict house prices. You have a dataset of 1000 house prices. How would you split this data into training and testing sets using sklearn's train test split function? A. Train test split x, y, test size 0.2, random state 42. B. Train test split x, y, test size 0.8, random state 42. C. Train test split x, y, test size 0.5, random state 42. D. All of the above. Correct. This option correctly uses train test split to split the data into training and testing sets. Test size 0.2 means 20 of the data will be used for testing, and the remaining 80 for training. Random state 42 ensures consistent splitting for reproducibility. Train test split function for data splitting. Test size parameter for controlling the test data proportion. Random state parameter for reproducible splitting. Correct. Similar to option A, this option uses train test split for data splitting. However, test size 0.8 means 80 of the data will be used for testing, and the remaining 20 for training. Random state 42 maintains reproducibility. Train test split function for data splitting. Test size parameter for controlling the test data proportion. Random state parameter for reproducible splitting. Correct. This option also utilizes train test split for data splitting, with test size 0.5 meaning 50 of the data will be used for testing, and the other 50 for training. Random state 42 guarantees reproducibility. Train test split function for data splitting. Test size parameter for controlling the test data proportion. Random state parameter for reproducible splitting. Correct. All of the above options are valid ways to split the data using train test split. The choice of test size depends on the desired proportion of data allocated for testing, while random state ensures consistent splitting across different runs. Flexibility of train test split in handling different test data proportions. Random state parameter for reproducible splitting. D. All of the above. Machine learning is a field of computer science that allows computers to learn from data without explicit programming. It involves algorithms that can identify patterns and make predictions based on training data. A type of machine learning where the algorithm learns from labeled data, meaning each input is paired with a corresponding output. The goal is to learn a function that maps inputs to outputs. A type of supervised learning task where the goal is to predict a continuous output variable based on input features. House price prediction is a regression problem. The data used to train a machine learning model. It consists of labeled examples that the algorithm uses to learn patterns and relationships. Data used to evaluate the performance of a trained machine learning model. It's a set of examples that the model hasn't seen before, and its performance on this data indicates how well it generalizes to unseen data. The process of assessing the performance of a trained machine learning model. It involves using metrics like accuracy, precision, recall, and F1 score to understand how well the model performs. Predicting the price of a house based on various factors like size, location, number of bedrooms, bathrooms, etc. Identifying customers who are likely to stop using a service or product. This can be used to design retention strategies and improve customer satisfaction. Classifying emails as spam or legitimate based on their content, sender, and other features. Identifying fraudulent transactions in financial systems by analyzing patterns in spending behavior and other financial data. Predicting the likelihood of a disease based on patient data such as symptoms, medical history, and test results. What is the primary purpose of grid search CV in scikit-learn? A. To split the data into training and testing sets for model evaluation. B. To automatically select the best hyperparameters for a machine learning model. C. To perform feature scaling and normalization on the data. D. All of the above. Grid search CV explained. Incorrect. While grid search CV does involve splitting data for evaluation, its primary purpose is not data splitting. It's about tuning hyperparameters, not dividing the data itself. Model evaluation, cross-validation, machine learning models. Grid search CV explained. Correct. Grid search CV's core function is to search through a grid of hyperparameter values and find a combination that yields the best performance on the model. Hyperparameter tuning. Machine learning models. Hyperparameters. For a support vector machine SVM model, you might use grid search CV to find the optimal values for the C regularization parameter and gamma kernel coefficient hyperparameters. Grid search CV explained. Incorrect. Feature scaling and normalization are preprocessing steps that are typically done before grid search CV, not by grid search CV itself. It focuses on tuning hyperparameters, not data transformation. Machine learning models. Hyperparameters. Grid search CV explained. Incorrect. Grid search CV is specifically designed for hyperparameter tuning, not data splitting or preprocessing. Model evaluation. Cross-validation. Machine learning models. Hyperparameters. B. To automatically select the best hyperparameters for a machine learning model. What is the difference between having grid search CV and grid search CV in scikit-learn? Which of the following statements is true regarding having grid search CV? A. Having grid search CV runs grid search CV on a subset of the data, selecting the best parameters, and then runs grid search CV on the full dataset using only the best parameters. B. Having grid search CV first performs an initial grid search on a reduced dataset and iteratively reduces the search space based on the best performing models, halving the number of parameter combinations at each step. C. Having grid search CV utilizes the same parameter combinations as grid search CV, but uses a different scoring metric. D. Having grid search CV is simply an alias for grid search CV. E. All of the above. LT font style font size 16 px GT LTBGTA LTBGT. Having grid search CV runs grid search CV on a subset of the data, selecting the best parameters, and then runs grid search CV on the full dataset using only the best parameters. LT font GT. Incorrect. Having grid search CV does not perform grid search CV on the full dataset after selecting the best parameters from a subset. It iteratively reduces the search space based on performance, halving the parameter combinations at each step. LT font style font size 16 px GT LTBGTB LTBGT. Having grid search CV first performs an initial grid search on a reduced dataset and iteratively reduces the search space based on the best performing models, halving the number of parameter combinations at each step. LT font GT. Correct. This statement accurately describes the working principle of having grid search CV. It starts with a reduced dataset, performs grid search, eliminates half of the parameter combinations based on performance, and repeats this process until a desired level of reduction is achieved. LT font style font size 16 px GT LTBGTC LTBGT. Having grid search CV utilizes the same parameter combinations as grid search CV, but uses a different scoring metric. LT font GT. Incorrect. Having grid search CV and grid search CV typically use the same scoring metric. The difference lies in the strategy of searching the parameter space, not the scoring metric used. LT font style font size 16 px GT LTBGTD LTBGT. Having grid search CV is simply an alias for grid search CV. LT font GT. Incorrect. Having grid search CV is not an alias for grid search CV. It's a distinct class in scikit-learn that implements a more efficient search strategy compared to grid search CV. LT font style font size 16 px GT LTBGTE LTBGT. All of the above. LT font GT. Incorrect. Since most of the statements are incorrect, this option is also incorrect. B. Hyperparameter tuning. LT font style font size 16 px hyperparameter tuning LTBRGT, finding the optimal values for model parameters that maximize performance. LT font GT. Hyperparameter tuning is the process of finding the best set of values for model parameters that control the learning process itself, not the parameters learned from the data. Examples include learning rate in gradient descent, the number of hidden layers in a neural network, or the penalty parameter in regularization. Grid search CV. LT font style font size 16 px grid search CV LTBRGT exhaustively searches a predefined parameter. Grid. LT font GT. Grid search CV exhaustively tries all possible combinations of hyperparameters within a predefined grid. It trains and evaluates the model for each combination, reporting the best performing set of hyperparameters based on a chosen metric. It can be computationally expensive for large parameter grids. Halving grid search CV. LT font style quote font size 16 px quotient halving grid search CV LTBRGT efficient grid search that reduces the parameter space iteratively. LT font GT. Halving grid search CV addresses the computational cost of grid search CV by starting with a reduced dataset and halving the number of parameter combinations at each iteration based on model performance. This makes it significantly faster and more scalable for large parameter spaces. Machine learning model optimization. LT font style quote font size 16 px quote GT machine learning model optimization LTBRGT tuning hyperparameters. For improved performance, LT font GT tuning hyperparameters is essential to get the most out of machine learning models. For example, adjusting the regularization strength in a linear regression model can help prevent overfitting and improve generalization performance. Deep learning model optimization. LT font style quote font size 16 px quotient deep learning model optimization LTBRGT finding the best learning rate, batch size, and other hyperparameters. LT font GT. Deep learning models often have many hyperparameters, including the learning rate controls how quickly the model updates its weights, batch size number of samples used for each gradient update, and the architecture number of layers, neurons per layer. Tuning these parameters can significantly impact training speed and model accuracy. Natural language processing NLP model optimization. LT font style quote font size 16 px quote GT natural language processing NLP model optimization LTBRGT tuning hyperparameters for language models. LT font GT. NLP models like transformers often involve hyperparameters related to the embedding size, number of attention heads, and dropout rate. Optimizing these parameters can improve model performance on tasks like text classification, sentiment analysis, and machine translation. Which of the following statements best describes the functionality of the sklearn model selection? Parameter grid class. It provides a grid-like structure to store and manage model hyperparameters. It generates a list of parameter combinations for a model, used in grid search cross-validation. It performs automatic optimization of hyperparameters using gradient descent. It splits the data into training and testing sets. All of the above. It provides a grid-like structure to store and manage model hyperparameters. False. While parameter grid deals with hyperparameters, its primary function is not storage. It primarily focuses on generating combinations for exploration, not storage. It generates a list of parameter combinations for a model, used in grid search cross-validation. True. This is the core function of parameter grid. It generates a list of parameter combinations, which are then used by grid search CV to systematically try out different hyperparameter settings. During cross-validation, it performs automatic optimization of hyperparameters using gradient descent. False. Parameter grid itself doesn't perform optimization. It only generates combinations. Optimization is done by algorithms like grid search CV or randomized search CV, which use gradient descent or other optimization methods internally. It splits the data into training and testing sets. False. Parameter grid is not involved in data splitting. Data splitting is typically done by functions like train test split within sklearn, model selection. All of the above. False. Since options A, C, and D are incorrect, this option is also incorrect. B. It generates a list of parameter combinations for a model, used in grid search cross-validation. Hyperparameters. Settings that control the learning process of a machine learning model, but are not learned from data. Example: learning rate in gradient descent. In a neural network, you can adjust the learning rate, a hyperparameter, to control how quickly the model learns from data. A higher learning rate leads to faster learning but may cause instability, while a lower learning rate ensures stability but might take longer to converge. Model parameters. Values learned from data during training. They define the model's internal structure and representation. In a linear regression model, the model parameters are the coefficients weights that multiply the input features to predict a output. The model learns these coefficients from the training data. Cross-validation. A technique to evaluate model performance by dividing the data into multiple folds and training and testing the model on different combinations of folds. In a spam detection model, cross-validation can be used to evaluate the model's performance on various sets of emails, ensuring that the model is robust and generalizes well to unseen data. Grid search. A method to find the best hyperparameter combination by trying out all possible combinations within a defined range. In a recommendation system, grid search can be used to find the best combination of hyperparameters for a collaborative filtering algorithm to improve the accuracy of personalized recommendations. Model evaluation. Assessing the performance of a trained model on a given dataset using metrics like accuracy, precision, recall, etc. In a fraud detection system, evaluating the model's performance on unseen data helps to determine its ability to correctly identify fraudulent transactions and minimize false positives. Model selection. Choosing the best model from a set of candidate models based on performance evaluation metrics. In a sentiment analysis task, you might experiment with different machine learning models like naive Bayes, support vector machines, and deep learning models, and then select the one that achieves the highest accuracy on the sentiment classification task. Parameter grid. A class in sklearn, model selection that facilitates grid search by generating all possible combinations of hyperparameters, providing a structured approach for exploration. Imagine tuning a support vector machine SVM model. You want to test different combinations of C regularization parameter and gamma kernel parameter. Parameter grid helps in creating all possible combinations of these values, simplifying the grid search process. Grid search CV. A class in sklearn, model selection that combines grid search with cross-validation, automatically finding the best hyperparameter combination based on the performance metrics. In a machine learning project for predicting customer churn, grid search CV can be used to optimize a logistic regression model by trying out different combinations of regularization strengths and solver algorithms. Randomized search CV. A class in sklearn, model selection that randomly samples hyperparameter combinations from a given distribution. It can be more efficient than grid search CV when dealing with a large number of hyperparameters. When working with a complex deep learning model with many hyperparameters, randomized search CV can be used to quickly explore a wide range of hyperparameter values and identify promising combinations for further fine-tuning. Automated machine learning. The use of algorithms and tools to automate various stages of machine learning, including hyperparameter tuning, feature engineering, and model selection. In a predictive maintenance system, Automated machine learning can be used to build and optimize models that identify patterns in sensor data to predict potential machine failures, reducing downtime and maintenance costs. You are trying to find the optimal hyperparameters for a random forest model using grid search. Which sklearn function would you use to generate a set of parameter combinations to evaluate? A. Model selection, parameter sampler. B. Model selection, grid search CV. C. Model selection, randomized search CV. D. All the above. Generates a set of parameter combinations for a model using a random distribution. True. Parameter sampler can indeed be used to generate random combinations of parameters from a specified distribution. This is helpful for exploring a large search space. Exhaustively searches all possible combinations of parameters within a specified grid. True. Grid search CV performs a systematic search over a grid of parameter values. This ensures that all possible combinations are evaluated, which can lead to optimal performance. Randomly samples parameter combinations from a specified distribution. True. Randomized search CV randomly samples combinations from a distribution. It is less computationally expensive than grid search CV and often finds good enough parameter combinations quickly. All the mentioned functions can be used to generate a set of parameter combinations for hyperparameter tuning. They differ in their approach and application. True. The statement correctly summarizes the roles of all three functions: parameter sampler, grid search CV, and randomized search CV. Each has its strengths and weaknesses based on the specific needs of the hyperparameter tuning process. D. All the above. The process of finding the best set of hyperparameters for a machine learning model. Optimizing the number of estimators in a random forest to balance bias and variance. Adjusting the learning rate in a gradient boosting model to avoid overfitting or underfitting. Generates a set of parameter combinations for a model using a random distribution. Exploring a large parameter space for a deep learning model by generating random sets of layer sizes and activation functions. Quickly evaluating different hyperparameter combinations for a support vector machine when the number of potential parameters is significant. Generating 5 random combinations of nestimators, number of trees and max depth, maximum depth of each tree for a random forest. From sklearn, model selection, import parameter sampler. Paramdust nestimators 50, 100. 200, 300, max depth 5, 10, 15, 20. Combinations parameter sampler paramdust, knitter 5, random state 42. For combination in combinations, print combination. Exhaustively searches all possible combinations of parameters within a specified grid. Finding the optimal values for C regularization parameter and kernel in a support vector machine. Thoroughly testing different combinations of alpha regularization strength and penalty in a logistic regression model to achieve the best model complexity. Exploring a grid of C values 0.1, 1, 10 and gamma values 0.01, 0.1. 1 for a support vector machine with an RBF kernel. From sklearn, model selection, import grid search CV. From sklearn.svm, import svc. Paramgrid C 0.1, 1, 10, gamma 0.01, 0.1, 1. Grid search CV svc kernel RBF. Paramgrid CV5, grid search, fit X-train, Y-train, print grid search, best params. Randomly samples parameter combinations from a specified distribution. Quickly finding a good set of hyperparameters for a neural network model with a large number of layers and neurons. Efficiently evaluating different combinations of max features, number of features considered at each split, and min samples, split minimum samples required to split a node in a random forest. Randomly sampling 10 combinations of estimators uniformly distributed between 50 and 500 and max depth log uniformly distributed between 5 and 20 for a random forest. From sklearn, model selection, import randomized search CV. From sklearn, ensemble, import random forest classifier. Parameterized estimators, index for x in NP. Linspace start 50. Stop 500. Num 10. Max depth index for x in NP. Log space start tnp.log 105. Stop np.log 1020. Num 10. Random search, randomized search CV, random forest classifier. Param distributions, paramdist. Nitter 10. CV5. Random search. Fit X train. Y train. Print random search. Best params. Ideal for a quick exploration of parameter space, especially when the search space is vast. Quickly experimenting with various combinations of regularization techniques and hyperparameters. For a deep learning model with a large number of layers and neurons. Which of the following options accurately describes the primary purpose of randomized search CV in this context? To identify the best hyperparameters for a machine learning model by exhaustively testing all possible combinations. To perform cross-validation on a machine learning model with a fixed set of hyperparameters. To randomly sample hyperparameter combinations and evaluate their performance on a validation set. To optimize the model's architecture based on the training data. All of the above. A. To identify the best hyperparameters for a machine learning model by exhaustively testing all possible combinations. Incorrect. While randomized search CV aims to find the best hyperparameters, it doesn't exhaustively test all combinations. It uses random sampling to explore the search space more efficiently. A. LT font style quote font size 14 px quote GT LTBGT A. LTBGT to identify the best hyperparameters for a machine learning model by exhaustively testing all possible combinations. LT font GT. B. To perform cross-validation on a machine learning model with a fixed set of hyperparameters. Incorrect. Randomized search CV does not focus on cross-validation with a fixed set of hyperparameters. It's about tuning the hyperparameters by evaluating various random combinations. B. LT font style quote font size 14 px quote GT LTBGTB. LTBGT to perform cross-validation on a machine learning model with a fixed set of hyperparameters. LT font GT. C. To randomly sample hyperparameter combinations and evaluate their performance on a validation set. Correct. Randomized search CV's core functionality is to randomly sample hyperparameter combinations and evaluate their performance on a validation set to determine the best combination. C. LT font style quote font size 14 px quote GT LTBGTC. LTBGT to randomly sample hyperparameter combinations and evaluate their performance on a validation set. LT font GT. D. To optimize the model's architecture based on the training data. Incorrect. Randomized search CV focuses on finding the best hyperparameters for a chosen model structure. It doesn't optimize the model's architecture itself. D. LT font style quote font size 14 px quote GT LTBGTD. LTBGT to optimize the model's architecture based on training data. LT font GT. E. All of the above. Incorrect. Option C is the only accurate description of randomized search CV's purpose. ELT font style font size 14px GT LTBGTE. LTBGT all of the above alt font GT. C. Hyperparameter tuning. The process of finding the optimal values for hyperparameters that control a machine learning model's behavior. LT font style font size 14px GT LTBGT hyperparameter tuning LTBGT the process of finding optimal values for hyperparameters that control a machine learning model's behavior. LT font GT. Grid search. An exhaustive search technique that tries all possible combinations of hyperparameter values within a specified range. LT font style font size 14px GT LTBGT grid search LTBGT an exhaustive search technique that tries all possible combinations of hyperparameter values within a specified range. LT font GT. Cross-validation. A technique for evaluating a machine learning model's performance by dividing the data into multiple folds and using each fold as a validation set while training on the remaining folds. LT font style font size 14px GT LTBGT cross-validation LTBGT a technique for evaluating a machine learning model's performance by dividing the data into multiple folds and using each fold as a validation set while training on the remaining folds. LT font GT. Validation set. A portion of the data used to evaluate the model's performance during hyperparameter tuning. LT font style font size 14px GT LTBGT validation set LTBGT a portion of the data used to evaluate the model's performance during hyperparameter tuning. LT font GT. Distributions. Used to specify the range and probability of selecting specific hyperparameter values. LT font style font size 14px GT LTBGT distributions LTBGT used to specify the range and probability of selecting specific hyperparameter values. LT font GT. Predicting customer churn. By tuning hyperparameters of a churn prediction model, you can improve the model's accuracy in identifying customers likely to churn, allowing businesses to take proactive steps to retain them. LTULGT. LTLIGT predicting customer churn. LTLI fraud detection LTLIGT. LTLIGT image classification LTLIGT. LTLIGT natural language processing LTLIGT. LTULGT. Fraud detection. Optimizing fraud detection models through hyperparameter tuning helps identify suspicious transactions more accurately, reducing false positives and improving the effectiveness of fraud prevention strategies. LTULGT. LTLIGT predicting customer churn. LTLI fraud detection LTLIGT. LTLIGT image classification LTLIGT. LTLIGT natural language processing LTLIGT. LTULGT. Image classification. Hyperparameter tuning plays a crucial role in achieving high accuracy in image classification models. Fine-tuning hyperparameters like the number of layers in a convolutional neural network can enhance the model's ability to distinguish between different image categories. LTULGT. LTLIGT predicting customer churn. LTLI fraud detection LTLIGT. LTLIGT image classification LTLIGT. LTLIGT natural language processing LTLIGT. LTULGT. Natural language processing. Natural language processing tasks, such as sentiment analysis and text summarization, benefit significantly from hyperparameter tuning. Optimizing hyperparameters in models like recurrent neural networks can improve their ability to understand and process human language effectively. LTULGT. LTLIGT predicting customer churn. LTLI fraud detection. LTLIGT. LTLIGT image classification. LTLIGT. LTLIGT natural language processing. LTLIGT. LTULGT. Which of the following statements is true about halving random search CV in scikit-learn? A. It performs a random search over a specified parameter space, but it halves the number of candidates at each iteration. B. It uses a halving strategy to reduce the number of models evaluated, but it does not use random search. C. It is a hybrid approach that combines random search with a halving strategy to efficiently explore the parameter space. D. It is similar to randomized search CV, but it allows for specifying a fixed number of iterations. False. While halving random search CV does use random search, it doesn't simply halve the number of candidates at each iteration. It uses a more sophisticated strategy based on performance. False. Halving random search CV combines both halving strategy and random search. It's not just about reducing the number of models, but also exploring the parameter space efficiently. True. Halving random search CV is indeed a hybrid approach. It performs random search over the parameter space, but it employs a halving strategy to iteratively reduce the number of candidates based on their performance, thus efficiently exploring the parameter space. This makes it more efficient than simply evaluating all candidates. False. While both halving random search CV and randomized search CV are for hyperparameter tuning, halving random search CV uses a halving strategy that is not found in randomized search CV. It also doesn't allow for specifying a fixed number of iterations. It automatically determines the number of iterations based on the specified resource and factor. C. It is a hybrid approach that combines random search with a halving strategy to efficiently explore the parameter space. Halving random search CV in scikit-learn is a technique for hyperparameter optimization that combines the advantages of random search and a halving strategy. It effectively explores a large parameter space by iteratively reducing the number of candidate models based on their performance, thereby making it more efficient than evaluating all candidates at once. Optimizing hyperparameters for deep learning models with a large search space. Finding optimal parameters for complex machine learning models with limited computational resources. Efficiently exploring the parameter space of a model with many hyperparameters. Let's say we want to find the best parameters for a support vector machine SVM model with a parameter space defined as follows. Python. Paramgrid C 0.1. 1. 10. 100. Kernel linear. RBF. Gamma 0.1. 1. 10. Using halving random search CV, we would start by training a certain number of models with randomly sampled combinations from this parameter space. Based on their performance, we would then reduce the number of candidates by half, focusing on the better performing models. This process would repeat until a desired level of performance or budget is reached. Random search is a hyperparameter tuning technique that randomly samples combinations of parameters from a predefined distribution. This approach is often preferred for exploring large parameter spaces, as it is less prone to getting stuck in local optima compared to grid search. Optimizing the hyperparameters of a model with many parameters. Finding the optimal learning rate for a deep learning model. Exploring the hyperparameter space of a model with various nonlinear components. Efficiently searching for optimal hyperparameters when the relationship between parameter values and model performance is unclear. Consider a linear regression model where we want to tune the regularization parameter alpha to avoid overfitting. We can use random search to sample different values for alpha from a uniform distribution between 0.01 and 1.0. This allows us to explore a range of values for alpha without evaluating every possible combination, saving computation time. The halving strategy is a method for reducing the number of candidate models during hyperparameter tuning. It works by initially training a larger set of models with randomly sampled parameters. Then, the models are sorted based on their performance, and the lower performing half are discarded. This process continues until a desired level of performance or a limited budget is reached. This approach is effective for efficiently exploring a parameter space and finding optimal hyperparameters. What does the cross-validate function in sklearn model selection do? It splits the data into a training set and a test set. It evaluates a machine learning model using cross-validation technique. It trains a machine learning model on the given data. All of the above. It splits the data into a training set and a test set. This is partially correct. Cross-validate does involve splitting the data, but it splits it into multiple folds for cross-validation, not just a single train test split. It begins by splitting your dataset into multiple folds. It evaluates a machine learning model using cross-validation technique. This is also partially correct. Cross-validate uses cross-validation to evaluate a model, but it also trains the model and splits the data as part of the process. For each fold, it trains the model on all the other folds and evaluates its performance on that specific fold. It trains a machine learning model on the given data. This is correct. Cross-validate trains the model on different folds of the data as part of the cross-validation process. For each fold, it trains the model on all the other folds and evaluates its performance on that specific fold. All of the above. This is the correct answer. Cross-validate performs all of the above, splits the data, trains the model, and evaluates its performance using cross-validation. Cross-validate is a comprehensive function that performs various tasks related to model evaluation. All of the above. Cross-validation, a technique used to evaluate the performance of a machine learning model by splitting the data into multiple folds and training and evaluating the model on different combinations of folds. This helps in getting a more robust estimate of the model's performance on unseen data. Model selection, hyperparameter tuning, evaluating model performance on unseen data. Folds, the subsets of the data that are created during cross-validation. Each fold is used for both training and testing the model. Cross-validation, train-test split, a basic technique used in machine learning where the data is split into two sets: a training set used to train the model and a test set used to evaluate its performance. Cross-validation 1, 2, 0, 2, 4, 1, 3, 6, 0, 4, 8, 1, 5, 10, 0, 5. Imagine we have this data and want to use 5-fold cross-validation. We split the data into 5 folds, each containing one data point. For each fold, we train a model using the data from the other 4 folds and evaluate its performance on the held out fold. We repeat this for all 5 folds and average the performance metrics to get a more robust evaluation of the model. What does sklearn's cross-val predict function achieve in machine learning? A. Predicts target values using cross-validation. returning predictions on the same data used for training. B. Evaluates a model's performance using cross-validation, returning evaluation metrics. C. Splits data into training and testing sets using cross-validation. D. All of the above. True. LT font style font size 16px GT1. LTBGT prediction using cross-validation. LTBGT, it utilizes a specified cross-validation strategy like k-fold to partition the data. It then trains the model on each fold and predicts on the held-out fold. This results in predictions for all data points, even those used for training. LT font GT. True. LT font style font size 16px GT2. LTBGT evaluation through cross-validation. LTBGT by examining the predicted and actual values for each fold. You can calculate various evaluation metrics: accuracy, precision, recall, etc. This process provides a more robust assessment of the model's performance than traditional train test splits. LT font GT. True. LT font style font size 16px GT3. LTBGT data splitting. LTBGT, while not its primary function, the underlying mechanism of cross-validation naturally involves splitting the data into train and test sets. LT font GT. True. LT font style font size 16px GT cross-val predict is a versatile tool for model evaluation and prediction within a cross-validation framework. It performs all these tasks in a single function call, making it a powerful addition to your milliliter workflow. LT font GT. D. All of the above. LT font style font size 16px GT. LTBGT cross-validation. LTBGT, a technique for evaluating model performance by splitting data into multiple folds and training on a subset while testing on the remaining fold. This helps to reduce bias and provides a more generalizable estimate of the model's performance. LT font GT. Imagine you have a dataset of 100 samples. Using 5-fold cross-validation, you split the data into 5 folds of 20 samples each. You then train the model on 4 folds and test it on the remaining fold. This process is repeated 5 times, using a different fold for testing each time. The final performance is the average of the results across all 5 folds. LT font style font size 16px GT. LTBGT fold cross-validation. LTBGT, a popular cross-validation strategy where the data is divided into k-equal folds. The model is trained on k1 folds and tested on the remaining fold. This process is repeated k times, with each fold serving as the test set once. LT font GT. In 5-fold cross-validation, you'd have K5. Each fold would contain 20 of the data, and the model would be trained on 80 of the data and tested on the remaining 20. LT font style font size 16px GT. LTBGT evaluation metrics. LTBGT quantitative measures used to assess model performance. Examples include accuracy, precision, recall, F1 score, AUC, etc. The choice of metric depends on the specific problem and objectives. LT font GT. For a spam detection model, you might use precision and recall as metrics to evaluate how well the model identifies spam emails. For a medical diagnosis model, you might prioritize sensitivity recall to ensure the model accurately identifies patients with a condition. LT font style font size 16px GT. LTBGT hyperparameter tuning. LTBGT, the process of finding the best values for a model's hyperparameters, which control the model's learning process. It involves searching for a set of hyperparameters that optimizes the model's performance on a given dataset, LT font GT. For a support vector machine SVM model, you might tune the regularization parameter C to control the trade-off between fitting the training data and avoiding overfitting. Using cross-val predict, you could evaluate the model's performance for different values of C and select the best performing value. LT font style font size 16 px GT LTBGT model selection LTBGT, the process of choosing the best model for a specific problem. Comparing different machine learning algorithms based on their performance and suitability for a task. LT font GT. When predicting customer churn, you might compare the performance of a logistic regression model, a decision tree, and a neural network using cross-val predict. The algorithm that achieves the highest accuracy or best F1 score would be selected as the best model. LT font style font size 16 px GT1. LTBGT hyperparameter tuning. LTBGT cross-val predict allows you to evaluate the model's performance with different hyperparameter settings. This assists in finding the optimal configuration for your model. LT font GT. For a random forest model, you might tune the number of trees estimators and the maximum depth of each tree max depth. Using cross-val predict, you could evaluate the model's performance with various combinations of these hyperparameters and identify the setting that results in the best performance on a held-out dataset. LT font style font size 16 px GT2. LTBGT model selection. LTBGT, you can compare the performance of different machine learning algorithms by applying cross-val predict and evaluating them using appropriate metrics. LT font GT. When predicting customer churn, you might compare the performance of a logistic regression model, a decision tree, and a neural network using cross-val predict. The algorithm that achieves the highest accuracy or best F1 score would be selected as the best model. LT font style font size 16 px GT3. LTBGT OUT of sample predictions. LTBGT get reliable predictions on unseen data using cross-validation, ensuring a more accurate representation of your model's generalization ability. LT font GT. In a fraud detection system, you might use cross-val predict to get predictions on new transactions. The model will have been trained and validated on past data, ensuring it can accurately detect fraudulent activity in new, unseen transactions. You are training a machine learning model to predict customer churn. You've split your data into training and testing sets. Which cross-validation technique from sklearn, model selection, cross-val score would you use to assess the model's performance on unseen data and avoid overfitting? A. Leave one out CV. B. K-fold. C. Stratified K-fold. D. All of the above. A. Leave one out CV. Leave one out CV is a valid cross-validation technique that uses each data point as a single test sample while the rest of the data is used for training. It is computationally expensive for large datasets. It is a valid method and helps to avoid overfitting but is not necessarily the most practical. False. A. Leave one out CV. B. K-fold. K-fold is another valid cross-validation technique that randomly divides the data into K-folds. The model is trained and tested K times, each time using a different fold for testing and the remaining folds for training. This is a more efficient method than leave one out CV. It is a valid method and helps to avoid overfitting but is not necessarily the most practical. False. B. K-fold. C. Stratified K-fold. Stratified k-fold is a variation of k-fold designed for datasets with imbalanced classes. It ensures that each fold has a similar distribution of classes as the original dataset. This helps to avoid bias and overfitting in scenarios where the classes are not evenly distributed. It is a valid method and helps to avoid overfitting but is not necessarily the most practical. False. C. Stratified k-fold. D. All of the above. All the techniques mentioned. Leave one out. CV. K-fold and stratified k-fold are valid cross-validation approaches provided by sklearn, model selection, cross-val score. They differ in how they split the data and how they handle imbalanced datasets. Cross-validation is crucial for assessing the model's generalization ability and avoiding overfitting. You can select the technique that best suits your specific problem and dataset. True. D. All of the above. D. All of the above. A technique for evaluating a machine learning model's performance by dividing the data into multiple folds subsets, training the model on a subset, and testing it on the remaining fold. This process is repeated multiple times, each time using a different fold as the testing set. A technique for evaluating a machine learning model's performance by dividing the data into multiple folds subsets, training the model on a subset, and testing it on the remaining fold. This process is repeated multiple times, each time using a different fold as the testing set. A situation where a model performs exceptionally well on the training data but poorly on unseen data. This indicates the model has memorized the training data rather than learning general patterns. A situation where a model performs exceptionally well on the training data but poorly on unseen data. This indicates the model has memorized the training data rather than learning general patterns. A function from sklearn that provides a convenient way to perform cross-validation and evaluate the performance of different machine learning models using various metrics, e.g. accuracy, precision, recall. A function from sklearn that provides a convenient way to perform cross-validation and evaluate the performance of different machine learning models using various metrics, e.g. accuracy, precision, recall. A cross-validation technique where each data point is used as a single test sample while the rest of the data is used for training. This method is computationally expensive for large datasets. A cross-validation technique where each data point is used as a single test sample while the rest of the data is used for training. This method is computationally expensive for large datasets. A cross-validation technique where the data is randomly divided into k-folds, and the model is trained and tested k times, each time using a different fold for testing and the remaining folds for training. This method is more efficient than leave one out. CV. A cross-validation technique where the data is randomly divided into k-folds, and the model is trained and tested k times, each time using a different fold for testing and the remaining folds for training. This method is more efficient than leave one out. CV. A variation of k-fold designed for datasets with imbalanced classes. It ensures that each fold has a similar distribution of classes as the original dataset. A variation of k-fold designed for datasets with imbalanced classes. It ensures that each fold has a similar distribution of classes as the original dataset. Predicting customer churn as in the question. Predicting customer churn as in the question. Evaluating image classification models. Evaluating image classification models. Analyzing text sentiment. Analyzing text sentiment. Which statement best describes the purpose of sklearn's learning curve function? A. Visualizes the impact of training data size on model performance. B. Measures the stability of model predictions on different data subsets. C. Evaluates the performance of different hyperparameter configurations. D. All of the above. Correct. The learning curve function in scikit-learn sklearn plots the model's performance, e.g. accuracy, error rate against the size of the training data. This helps visualize the impact of training data size on model performance. Refer to the section LT font color co 0000FF quote GTLT learning curve LT BGTLT font TGT in the diagram. Overfitting, underfitting. Detecting overfitting, underfitting by observing the performance plateauing or decreasing as the training data size increases. Choosing the right training data size for a particular problem by identifying the point where adding more data yields diminishing returns. Imagine training a linear regression model on a dataset with 100 data points. As you increase the training data size from 10 to 50 to 100, the learning curve can show how the model's accuracy changes. If the accuracy plateaus after a certain point, it suggests that adding more data won't significantly improve the model's performance. On the other hand, if the accuracy keeps improving as the training data size increases, it indicates that the model is still underfitting the data. Correct. The learning curve function uses cross-validation to evaluate model performance. Cross-validation splits the data into multiple folds, and the model is trained and tested on different combinations of these folds. This process helps measure the stability of model predictions on different data subsets. Refer to the section LT font color co 0000FF quote TGTLT model stability LT BGTLT font TGT in the diagram. Cross-validation. Identifying models prone to high variance by observing large fluctuations in performance across different data subsets. Understanding the impact of data variability on model predictions by analyzing the consistency of performance across different folds. Let's say you split the data into 5 folds for cross-validation. The learning curve function will train the model on 4 folds and test it on the remaining fold for each iteration. If the model's performance varies significantly across different folds, it suggests a high variance. On the other hand, if the performance is consistent, it indicates a stable model. Correct. The learning curve function can be used to evaluate the performance of different hyperparameter configurations. By running the function with different hyperparameters, you can compare their impact on the model's performance as the training data size changes. Refer to the section LT font color co 0000FF quote GTLT hyperparameter tuning LT BGTLT font TGT in the diagram. Hyperparameter tuning. Optimizing model performance by finding the best hyperparameters by analyzing the learning curves generated for different configurations. Choosing the right model architecture by comparing the learning curves for different architectures and hyperparameter settings. Suppose you are training a support vector machine SVM with 2 different hyperparameters, C and gamma. The learning curve function can help you determine the best combination of these parameters by comparing the learning curves for different values of C and gamma. The hyperparameters that result in the highest accuracy or lowest error rate on the learning curve would be considered optimal. Correct. All the above statements accurately describe the purpose of the learning curve function in scikit-learn. It helps visualize the impact of training data size, measure model stability, and evaluate hyperparameter configurations. Refer to the section LT font color co 0000FF quote GTLT sklearn, model selection, learning curve LT BGTLT font TGT in the diagram. learning curve, model stability, hyperparameter tuning, overfitting, underfitting, cross-validation, diagnosing and addressing overfitting and underfitting in machine learning models, optimizing model performance by selecting the appropriate training data size, tuning hyperparameters, and ensuring model stability, evaluating model capacity and generalization ability to understand how well a model will perform on unseen data. The learning curve function provides a comprehensive picture of model performance. By looking at the learning curve, you can identify if the model is overfitting or underfitting, how stable the model is, and if the hyperparameters are effectively tuned. In a real-time use case, imagine you are training a deep neural network for image classification. The learning curve can help you identify if the network is overfitting the training data, if you need more data to train the network, or if you should adjust the network's architecture or hyperparameters to improve performance. D. All of the above. Which of the following statements accurately describes the purpose of font color 0000FF sklearn, model selection, permutation test score font in machine learning? Estimates the significance of a model's performance by randomly shuffling target values and comparing the results to the original performance. Evaluates the stability of a model by repeatedly training and testing on different data splits. Calculates the variance in model performance across different random seeds. All of the above. Correct. This is the core function of permutation testing. It generates a distribution of scores assuming the model's performance is random, allowing you to assess the significance of the actual score. The font color 0000FF permutation test score font function is a powerful tool for assessing the statistical significance of a machine learning model's performance. It leverages the concept of permutation testing, a statistical technique that helps determine whether observed results are likely due to chance or a genuine effect. This is achieved by repeatedly shuffling the target variable labels and evaluating the model's performance on these shuffled datasets. This process generates a distribution of scores under the null hypothesis that the model is no better than random. The original score is then compared to this distribution, and the p-value is calculated. A low p-value, typically less than 0.05, indicates that the observed performance is statistically significant and unlikely to be due to chance. Correct permutation testing helps assess model stability. By shuffling the target values, you are essentially creating various scenarios to see if the model's performance remains consistent. The font color 0000FF permutation test score font function is a powerful tool for assessing the statistical significance of a machine learning model's performance. It leverages the concept of permutation testing, a statistical technique that helps determine whether observed results are likely due to chance or a genuine effect. This is achieved by repeatedly shuffling the target variable labels and evaluating the model's performance on these shuffled datasets. This process generates a distribution of scores under the null hypothesis that the model is no better than random. The original score is then compared to this distribution, and the p-value is calculated. A low p-value, typically less than 0.05, indicates that the observed performance is statistically significant and unlikely to be due to chance. Correct. The repeated shuffling of target values effectively creates different random seeds, revealing the variance in model performance. The font color 0000FF permutation test score font function is a powerful tool for assessing the statistical significance of a machine learning model's performance. It leverages the concept of permutation testing, a statistical technique that helps determine whether observed results are likely due to chance or a Genuine effect. This is achieved by repeatedly shuffling the target variable labels and evaluating the model's performance on these shuffled datasets. This process generates a distribution of scores under the null hypothesis that the model is no better than random. The original score is then compared to this distribution, and the p-value is calculated. A low p-value, typically less than 0.05, indicates that the observed performance is statistically significant and unlikely to be due to chance. Correct. All three choices accurately describe aspects of permutation testing. It assesses significance, stability, and variance in model performance. All of the above. D. All of the above. A technique to assess the statistical significance of observed results by randomly shuffling data. It's useful for understanding if a model's performance is due to a genuine pattern or just chance. Determining if a new drug treatment is effective by comparing the treatment group's results to a group receiving a placebo. Analyzing the effectiveness of a marketing campaign by comparing sales data before and after a campaign. Assessing the impact of a new website design on user engagement by comparing metrics like time spent on site and conversion rates. A statement about the population that is assumed to be true until there is enough evidence to reject it. In permutation testing, the null hypothesis is that the model's performance is no better than random. Testing if the average height of men is different from the average height of women. Evaluating if there's a correlation between smoking and lung cancer. Determining if a new educational program improves student test scores. The probability of obtaining the observed results or more extreme results if the null hypothesis were true. A low p-value, typically less than 0.05, indicates evidence against the null hypothesis. In a clinical trial, a low p-value might indicate that the new drug treatment is effective. In a marketing experiment, a low p-value might indicate that the new campaign increased sales. In a website redesign, a low p-value might indicate that the new design improved user engagement. 1, 2, 1, 3, 4, 0, 5, 6, 1, 7, 8, 0, 9, 10, 1. Imagine you have a model that predicts a target value based on features. You could calculate your model's accuracy on this data. Now, to perform a permutation test, you'd shuffle the target values ones and zeros in this case. You'd then recalculate the accuracy of your model on this shuffled data. And repeat this process many times. The distribution of accuracies you get from these shuffles provides a baseline for comparing your original accuracy. If your original accuracy is significantly higher than most of the shuffled accuracies, then it suggests your model is capturing a real pattern in the data. What is the primary purpose of the validation curve function in scikit-learn? sklearn, model selection, validation curve. A. To evaluate the performance of a model on unseen data. B. To select the optimal hyperparameters for a model. C. To assess the model's stability across different data splits. D. All of the above. A. To evaluate the performance of a model on unseen data. Correct. Validation curve employs cross-validation, which involves splitting the data into training and testing sets. The model is trained on the training set and evaluated on the testing unseen set, providing insights into its generalization ability. Model evaluation. B. To select the optimal hyperparameters for a model. Correct. Validation curve systematically tests different values of a specified hyperparameter, e.g., regularization strength, learning rate, and assesses the model's performance. This aids in identifying the hyperparameter value that maximizes the model's effectiveness. Hyperparameter optimization. C. To assess the model's stability across different data splits. Correct. Validation curve evaluates the model's performance on multiple random data splits. The stability of performance across these splits indicates the model's robustness to data variations. Model stability. D. All of the above. Correct. Validation curve encompasses all three aspects: model evaluation on unseen data, hyperparameter optimization, and assessment of model stability. Answer D. All of the above. D. All of the above. Hyperparameters are settings that control the learning process of a machine learning model. For instance, in a support vector machine SVM, the regularization parameter C controls the trade-off between fitting the training data perfectly and achieving a model that generalizes well. Validation curve helps determine the optimal value for such hyperparameters by testing different values and measuring their impact on the model's performance. Assessing a model's performance on unseen data is crucial to ensure its ability to generalize beyond the training data. Validation curve utilizes cross-validation, which involves splitting the data into training and testing sets multiple times to evaluate the model's accuracy and generalization capabilities. A stable model consistently performs well across different data samples. Validation curve allows you to assess the consistency of a model's performance by evaluating it on multiple data splits. This helps identify if the model is significantly affected by random variations in the data. This refers to data that the model has not encountered during training. Evaluating the model on unseen data is critical to gauge its ability to generalize to new, previously unobserved data. In a fraud detection model, validation curve could be used to find the optimal value for the regularization strength of a logistic regression model. This would help balance the trade-off between minimizing false positives flagging legitimate transactions as fraudulent and minimizing false negatives failing to detect fraudulent transactions. In an image classification task, validation curve can be used to evaluate the performance of a convolutional neural network on a held-out set of images. This helps ensure the model can accurately classify new images that it hasn't seen during training. In a customer churn prediction model, validation curve can be used to assess the model's stability across different customer segments. This helps identify if the model is biased towards specific customer demographics or if its predictions are consistent across different groups. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 0, 1, 1, 0, 1. From sklearn, model selection import validation curve. From sklearn.svm import svc. Import numpy is np. Define the model in hyperparameter range. Model svc. Paramrange np. Log space -3. 3. 7. Calculate the validation curve. Train scores. Test scores validation curve model. X, Y. Paramname C. Paramrange. Scoring accuracy. Analyze the results e.g. Plot the validation curve. This code snippet demonstrates using validation curve to evaluate the accuracy of a support vector machine SVC model across different values of the regularization parameter C. The paramrange specifies a range of C values to test the function return scores for both training and testing data, allowing you to analyze how the model's performance changes with different C values. What is the purpose of learning curve display in scikit-learn? A. To visualize the performance of a machine learning model as the training set size increases. B. To display the confusion matrix of a machine learning model. C. To plot the distribution of features in a dataset. D. All of the above. True. The learning curve display class in scikit-learn is specifically designed to visualize the learning curve of a machine learning model. A learning curve plots the model's performance, e.g., accuracy, error against the size of the training set. This visualization helps you understand how the model's performance improves or plateaus as you increase the amount of training data. The learning curve display class in scikit-learn is specifically designed to visualize the learning curve of a machine learning model. A learning curve plots the model's performance, e.g., accuracy, error against the size of the training set. This visualization helps you understand how the model's performance improves or plateaus as you increase the amount of training data. False. The learning curve display focuses on the learning curve, not the confusion matrix. Confusion matrices are used to assess the model's performance by visualizing the true positives, true negatives, false positives, and false negatives, to display the confusion matrix of a machine learning model. False. Plotting feature distributions is generally handled by other visualization tools, such as histograms or box plots. Learning curve display is dedicated to showcasing the learning curve, not individual feature distributions. To plot the distribution of features in a dataset. False. Only option A is accurate. Options B and C describe different visualization tools. All of the above. A. Learning curve. A plot that shows how a machine learning model's performance changes with the size of the training set. A plot that shows how a machine learning model's performance changes with the size of the training set. Training set size. The number of data points used to train a machine learning model. The number of data points used to train a machine learning model. Model performance. A measure of how well a machine learning model is performing, such as accuracy, precision, recall, or F1 score. A measure of how well a machine learning model is performing, such as accuracy, precision, recall, or F1 score. Data size impact. Determine how much training data is needed for a model to perform well. Determine how much training data is needed for a model to perform well. Model complexity. Identify if the model is underfitting, not complex enough, or overfitting, too complex based on pay. Learning curve's shape. Identify if the model is underfitting, not complex enough, or overfitting, too complex based on pay. Learning curve's shape. Feature engineering. Evaluate whether adding more features to the model significantly improves performance. Evaluate whether adding more features to the model significantly improves performance. From sklearn, model selection import learning curve. From sklearn, model selection import learning curve display. Create a model, e.g., logistic regression. Model logistic regression. Generate learning curves. Train sizes. Train scores. Test scores. Learning curve. Model. X. Your features. Y. Your target variable. CV5. Number of cross-validation folds. Train sizes. NP. Linspace 0.1. 1.0. 10. Training set sizes. Scoring accuracy. Display the learning curves. Learning curve display. From estimator. Model. X. Y. Train sizes. Train sizes. Train scores. Train scores. Test scores. Test scores. Scoring accuracy. CV5. NJOBS1. This code snippet demonstrates how to generate and display learning curves using K. Learning curve display class in scikit-learn. 10, 20, 30, 40, 50, 0.6, 0.7, 0.8, 0.85, 0.9. Imagine you are training a model to classify emails as spam or not spam. You start with a small training set of 10 emails and observe an accuracy of 60. As you increase the training set size to 20 emails, the accuracy improves to 70. This pattern continues as you add more training data, suggesting that the model's performance is getting better with more data. A learning curve would plot these training set sizes on the x-axis and the corresponding accuracy scores on the y-axis, illustrating the relationship between data size and model performance. What is validation curve display? A visualization tool for exploring how a machine learning model's performance varies with a hyperparameter settings, a function that generates a dataset for hyperparameter tuning, a method for splitting a dataset into training and validation sets. All of the above. Correct validation curve display is indeed a visualization tool. Its primary purpose is to help you understand the performance of your model as you alter different hyperparameter settings. It's a visual way to pinpoint the optimal range for a specific hyperparameter, ultimately leading to better model performance. The diagram clearly states this purpose in the explanation section under the validation curve display. A visual guide heading. Hyperparameters. Imagine you are training a support vector machine SVM model. You want to find the best value for the C hyperparameter, which controls the trade-off between maximizing the margin and minimizing the classification error. You use validation curve display to plot the model's performance, e.g., accuracy across a range of C values. The plot reveals that the model performs best within a particular range of C. This helps you fine-tune the SVM model for better accuracy. Let's say you are using a logistic regression model with regularization strength as a hyperparameter. You want to find the optimal regularization strength C to prevent overfitting. Using validation curve display, you plot the model's performance, e.g., accuracy for different values of C. The plot might show that the model achieves the highest accuracy at C0.5, suggesting that this value balances model complexity and generalization. Incorrect. This description aligns more closely with the concept of a data generator or data augmentation technique. While hyperparameter tuning involves generating different model configurations, validation curve display doesn't directly create datasets. It focuses on visualizing the performance of already trained models. Data augmentation. Incorrect. Splitting a dataset into training and validation sets is a standard data preparation technique. Validation curve display assumes this is done beforehand and then analyzes the model's performance on the validation set across different hyperparameter values. Data splitting. Before using validation curve display, you would typically split your dataset into a training set used for model training and a validation set used to evaluate the model's performance. Validation curve display then uses the validation set to assess the model's performance across different hyperparameter values. Incorrect. While validation curve display is related to hyperparameters, it's not involved in generating datasets or splitting datasets. Option A accurately captures its function. A.